Hello, welcome back to this channel. Get comfortable, I mean it. Sit back, relax. We're about to go on a journey through space, through time, through the very fabric of reality. And trust me, it's bigger than anything you've imagined. You've looked up at the night sky, right? Thousands of stars, millions of galaxies, a universe so vast it makes you feel small. But what if I told you? The universe isn't just vast, it's growing, expanding, constantly. Space itself is stretching, right under your feet, around you, everywhere. You might think galaxies are moving through space, that they're flying away from us like rockets. Nope, not exactly. Galaxies aren't racing through a pre-existing void. The void itself is stretching, carrying galaxies along like raisins in rising bread dough. Every galaxy sees the same thing. Every dot on that cosmic dough sees every other dot moving away. And here's the crazy part. There's no center, no edge, no point zero where it all started. Space isn't expanding into something else. It is something else. Mind-bending, right? This expansion has been going on for 13.8 billion years, and it's not slowing down. Far from it. In fact, it's accelerating, faster and faster as time goes on. Something we call dark energy is pushing space outward. Invisible, mysterious, everywhere. It's tiny, but multiplied across billions of light years, it dominates everything. Think about it. Every inch of space you see, every star, every planet is being carried by this cosmic current. We are floating, moving, expanding without even realizing it. And here's where it gets personal. Because this expansion affects us too. Time stretches, distances grow. Everything we know is part of this cosmic rhythm. The universe isn't just growing outside of us. In a way, we are growing with it. We are part of this endless process. Every moment you exist, the universe is quietly stretching around you. Now, you might be asking, why should I care? Because understanding expansion changes everything. Your place in the cosmos, your perception of time, your understanding of reality. It's the key to the biggest questions. Where did we come from? How will it end? And what exactly does it mean to exist in a universe that never stops growing? In this series, we're going to explore it all, from the smallest quantum fluctuations to the fate of galaxies, from Einstein's mistakes to the mysteries of dark energy. We'll uncover how the universe grows, stretches, and evolves. And along the way, you'll see your own life in a new light. Because knowing that the universe itself is alive, expanding, creating, it puts everything into perspective. So, buckle up, keep your mind open, and get ready to witness the story of the universe as you've never seen it before. And if you're ready to see reality on a cosmic scale, hit that subscribe button, because this journey is just beginning, and trust me, you won't want to miss what's coming next. Long ago, humans looked up at the sky, and they thought the universe was eternal, static, unchanging. Stars stayed in place. Planets traced predictable paths. The cosmos was perfect, fixed, timeless. Aristotle thought the heavens were a perfect sphere. Plato imagined a harmonious cosmos, orderly and eternal. The idea was simple and comforting. The sky didn't move randomly. It followed a divine design. Nothing changed, nothing died, nothing grew. This thinking lasted for centuries. Then came Copernicus, the sun, not Earth, center of the solar system. Revolutionary, shocking, but even he imagined a mostly static universe. Planets moved, stars stayed put. The cosmos beyond Earth remained fixed. Then Galileo turned a telescope to the heavens. Moons orbiting Jupiter, phases of Venus. The universe wasn't as fixed as people thought. Yet the overarching view stayed the same. Stars and galaxies, solid, eternal. Then Newton arrived. Gravity explained planetary motion, perfect equations, predictable outcomes. He thought the universe was infinite, static, balanced, infinite space, infinite stars, static equilibrium, a machine-like cosmos. But there was a problem. Gravity, everywhere, pulling everything together. If the universe is infinite but static, gravity would pull all stars together, and the universe would collapse. Newton ignored it. He left it as a philosophical question. Fast forward to the 20th century. Einstein's general relativity entered the scene, a new way to describe gravity, space and time as a flexible fabric. Equations predicted something radical. The universe wasn't static. It should be expanding or contracting. Einstein didn't like that. He wanted a static universe. So he added the cosmological constant, a fudge factor, a push to counter gravity, perfect balance, static cosmos restored, and he called it his greatest blunder. Why? Because Hubble later proved the universe was expanding. All those stars, all those galaxies, moving away. The static cosmos was a myth. For centuries, humans clung to the idea of a fixed universe. It was intuitive, comforting, a place where everything had always existed. No surprises, no endings. Even after observations suggested otherwise, the idea lingered. It shaped science, philosophy, culture. People couldn't imagine a cosmos that grows, a cosmos that changes, a cosmos with a beginning and eventually an end. Even today, remnants of this thinking persist. People assume the universe is stable, constant, but the universe is dynamic. It moves, expands, evolves. Everything we once thought immutable is actually in flux. Time itself stretches, space itself grows. The heavens aren't fixed, they are alive. And understanding this history matters, because human misconceptions show how hard it is to grasp cosmic reality. They show the limits of intuition, and they prepare us for the next revelation. The universe is growing faster than anyone could have imagined. So, forget the static sky. The universe you see isn't eternal in the way humans once believed. It's dynamic, shifting, expanding every moment. And that expansion sets the stage for everything to come. From galaxies forming, to stars dying, to the ultimate fate of the cosmos. Next, we'll dive into the first clues that space itself is stretching. And trust me, those discoveries will blow your mind. So stay curious and keep watching. Let's talk about a subtle but mind-bending idea. The universe is expanding, but what's actually moving? Are galaxies racing through space? Or is space itself stretching? Big difference. And it changes everything we think about motion. Imagine a loaf of raisin bread, freshly baked, warm, rising in the oven. The dough expands. The raisins? They don't move on their own. They're carried apart by the expanding dough. That's space. The raisins are galaxies. Galaxies aren't racing through space like cars on a highway. They're sitting in space. Space itself is growing between them. The distance increases, naturally, automatically, no engine required. This is why two galaxies can appear to move faster than light. Crazy, right? Nothing is breaking the speed limit. It's not motion through space. It's space itself stretching, and that has strange consequences. Look at the cosmic redshift. Light from distant galaxies stretches as space expands. Wavelengths grow longer. Colors shift toward red. More redshift means more expansion. More redshift means further distance. More redshift means we see the galaxy as it was in the past. Expansion creates a time machine effect. We look back billions of years by measuring light. This is not motion like a car driving away. This is motion baked into the fabric of reality. It's geometry in action. Einstein's relativity predicted this. Space and time are flexible. Gravity shapes them. Energy moves them. The universe is not a static stage. It's a dynamic actor. Every galaxy sits on that stage, but the stage itself stretches, and stretching space changes our perspective. Galaxies far enough away seem to recede faster than closer ones. Distance matters. Scale matters. The farther out you look, the faster galaxies seem to fly away. Again, it's not speed through space. It's an expansion of space. Even empty space counts. Vacuum isn't nothing. It carries the expansion, and dark energy fuels it. A mysterious push that grows stronger as space stretches. This is why the universe accelerates. Galaxies move apart faster over time, not because they're fleeing, because the stage beneath them grows. This also explains cosmic horizons. Some galaxies are so far away, their light will never reach us. They're not gone. They're just beyond the edge of expanding space, forever unreachable. Space itself sets the limit. Even light can't bridge it. This is why expansion isn't intuitive. Our brains think in motion through space. We imagine rockets, cars, and balls, not expanding geometry. But the universe operates differently. Everything is relative. Distances, motion, and time all depend on the stretching of space itself. Even our cosmic clock feels it. Time slows for distant objects in rapid expansion. A galaxy at the edge of the observable universe ages more slowly than we do. Expansion doesn't just separate. It reshapes experience itself. It changes what now even means across cosmic distances. So remember, galaxies aren't sprinting through emptiness. They're passengers on space itself, and space is on a growth spree. The universe isn't a fixed arena. It's a living, breathing stage that expands continuously. This subtle distinction will help you understand the next chapters. Dark energy, cosmic acceleration, and the ultimate fate of everything. Because if you confuse galaxies with space, you'll miss the mind-blowing reality of how the cosmos truly evolves. Next, we'll explore how expansion bends time itself, stretching the universe not just in distance, but in the flow of moments. Strap in. Things are about to get weird. Time isn't as simple as you think. Tick-tock, seconds passing, minutes flying. We experience it as steady, constant, universal. But that's a local illusion. Einstein shattered that idea. Time flows differently depending on motion, and it changes depending on where you are in the universe. Let's start with motion. You've heard of time dilation. Fast-moving objects age more slowly. A spaceship zooming near light speed experiences less time than people back on Earth. A classic twin paradox. One twin rockets away, the other stays home. Years pass. The traveling twin returns younger. It's not science fiction. It's reality. Measured, verified. Now, imagine space itself is expanding. Galaxies are rushing away at unimaginable speeds. Not through space, but with space. Light from these galaxies is stretched, redshifted. The farther away a galaxy is, the faster it recedes. And here's the kicker. Time slows down for them. Way down. Events in those distant galaxies unfold more slowly, 10 times slower for some. You're watching their cosmic lives in slow motion. Time isn't universal. The universe has local nows. Your now is different from theirs. This creates a mind-bending reality. The age of the universe depends on perspective. From Earth, 13.8 billion years. From a distant galaxy moving away at near light speed, much younger. Time itself is stretched. Cosmic expansion doesn't just pull galaxies apart. It stretches time like taffy. The early universe was dense, space compact. Time flowed faster. Stars formed. Galaxies emerged. Black holes ignited, all at an accelerated cosmic pace. Expansion reshaped not just distances, but the rhythm of events. And simultaneity? Forget it. Two events that seem simultaneous here. They're not simultaneous there. The universe has no universal now. Every observer experiences their own timeline. This sounds theoretical, but we see it in light from distant galaxies, red-shifted, stretched, slow-motion events. The farther we look, the farther back in time we see. We're literally looking at the past. Light from the first galaxies shows time flowing differently, and dark energy complicates it further. As expansion accelerates, the time dilation grows. Future civilizations will see distant galaxies almost frozen in time, a snapshot of cosmic history stretched to eternity. This gives a new way to understand cosmic evolution. Time is compressed in the early universe. Processes we think take billions of years happened in a fraction of that. Stars, galaxies, black holes born in fast forward. Understanding this is crucial for predicting the universe's fate, because if expansion stretches time, it also stretches causality, horizons, and even the very fabric of reality. Eventually, in extreme scenarios like the Big Rip, time itself may unravel alongside space. Relativity teaches us that motion and location aren't just details. They define the flow of events, the evolution of galaxies, the lifespan of stars, and even the experience of cosmic moments. Your cosmic clock isn't universal. It's local, personal, relative. Next, we'll explore how this stretching of time interacts with the universe's expansion, dark energy, and the ultimate fate of all matter. Buckle up. Time itself is about to get stranger. Ever wondered what it would be like to watch a galaxy far, far away? Not through a telescope lens, but through time itself. Strap in, because the universe isn't just stretching space, it's stretching time. We call this cosmic time dilation. Light from distant galaxies doesn't just travel across space, it travels across expanded space. And the farther it comes from, the slower the galaxy's events appear. Imagine a galaxy at the edge of our observable universe. Light left it billions of years ago. It's redshifted tenfold. That means its motion, its stars, its explosions all appear 10 times slower to us. A supernova that would take days in its own galaxy takes months in our telescopes. Time itself has been stretched along with space. This isn't just theory. Astronomers measure it, observe it, confirm it. Cosmic time dilation gives us a front row seat to the early universe. The young cosmos was a fast-paced place. Stars formed quickly, galaxies collided, black holes devoured matter, all in a fraction of the time we see today. It's like watching a cosmic fast-forward, then slowing it down to human perception. But here's where it gets philosophical. If time flows differently everywhere, how old is the universe really? From Earth, 13.8 billion years. From a galaxy hurtling away near light speed, much younger. Time is relative, not absolute. Each location, each speed, has its own clock. Many wonder Brestinders, the Rastagoich divisant, and the stretching continues. Dark energy accelerates expansion. As galaxies recede faster, their events slow even more. Someday, distant galaxies will appear almost frozen in time, a cosmic tableau locked in place. We might never see their evolution beyond a certain point. This creates a paradox. The universe is dynamic, always changing, yet parts of it will appear timeless. We see only slices of history, shaped by distance, motion, and expansion. Even our most powerful telescopes can't bypass this effect. Cosmic time dilation sets fundamental limits on observation. It's nature's way of revealing both the past and the scale of the universe simultaneously. The early universe was a crucible. High density, compressed space, compressed time. Stars ignited faster. Galaxies formed quickly. Black holes grew rapidly, all because cosmic clocks ticked differently. We're witnessing the universe's life in slow motion, a cinematic reel of cosmic history, and it teaches us a profound truth. Time is not a single river, it's a landscape, flowing differently depending on where you are. This challenges our assumptions. What we perceive as now is just our local window. Other observers, elsewhere, have different nows. Cosmic events are relative, both in space and time. Next, we'll explore how we actually measure this cosmic slowdown, from supernovae to redshift, and how it helps us map the universe's expansion with stunning precision. Buckle up. The universe isn't just getting bigger, it's getting slower and stranger the farther you look. Close your eyes for a second. Picture the universe at its birth. Not 13.8 billion years later, but moments after the Big Bang. Space was tiny, dense beyond imagination. Matter is packed tightly. Energy swirled violently. Time didn't flow like it does now. It raced. Cosmic processes that today take billions of years happened in a flash. Stars, galaxies, black holes, they all grew up fast. The early universe was a cosmic pressure cooker. Everything unfolded at breakneck speed. Why? Because the universe wasn't just smaller. It was compressed in time as well as space. Light from distant galaxies shows us echoes of that fast-paced past. We see young galaxies forming, stars igniting, and supernovae exploding all in rapid succession. From our vantage point, it looks slow due to cosmic time dilation. But back then, it was chaotic, intense, alive. The first star's population, 3 stars, burned hotter and faster than anything we see today. Massive, short-lived, and brilliant. Their deaths seeded the cosmos with heavy elements. Galaxies formed, merged, collided, and evolved in mere millions of years. Compare that to today. Galaxies grow over billions of years, a slow dance across cosmic time. The early universe was hyperactive. Even black holes formed fast. Supermassive black holes that now lurk in galaxy centers grew astonishingly quickly. We're still puzzling over how they formed so fast in such a compressed environment. Every cosmic process was accelerated by the density and energy packed into the small, early cosmos. Expansion hasn't just stretched space, it has stretched time itself. As the universe grew, processes slowed. Time became normal for our region, ticking at the pace we experience today. This compression explains why the cosmic microwave background exists. It's a snapshot of the universe when it was tiny, hot, and fast. We can read it like a cosmic diary. Each fluctuation in temperature, each pattern, tells us how matter and energy behaved in that compressed era. Even fundamental forces acted differently. The early universe was a laboratory for physics under extreme conditions. Nuclear reactions forged the first elements. Hydrogen, helium, trace lithium, they all formed within the first few minutes. That's faster than any process we see in the modern cosmos. Cosmic inflation, if it happened, further compressed time and space, stretching the universe while simultaneously speeding up processes in its densest moments. Every explosion, every collision, every formation event occurred in a blink compared to today. Yet, through cosmic time dilation, these events appear to us in slow motion. It's a universe of extremes, fast on its own clock, slow to our eyes. And it teaches us a critical lesson. History is relative. Time isn't universal. It's intertwined with space, motion, and expansion. By studying these compressed early moments, astronomers can map how the universe evolved from a dense, chaotic stew to the vast, structured cosmos we inhabit now. We begin to understand the rhythm of cosmic life: compressed birth, slower adolescence, and the steady maturation of galaxies, stars, and planets. The early universe shows us that speed and scale are relative. Everything we see today, our sun, our galaxy, our universe itself, emerged from a period when time itself was accelerated. Understanding that era is like holding a stopwatch on creation itself. It's fast, furious, and utterly essential to grasping the universe as it is today. Close your eyes and travel back, way back, to the first billion years after the Big Bang. The universe is young, dense, and restless. Space is smaller, matter is packed tighter, and time itself flows differently. In this cosmic crucible, stars and galaxies don't take their time, they sprint. Gravity pulls gas and dust together faster than we can imagine. Clouds collapse in a flash. Fires ignite. The first star's massive, short-lived, brilliant burst into existence. These stars are unlike anything we see today. They burn hotter, brighter, and faster. They live for a few million years, a heartbeat in cosmic terms, then die in titanic explosions. Supernovae scatter the first heavy elements across space. Without these early deaths, galaxies could never form properly. The universe is a workshop. Matter is forged, recycled, and sculpted into structure at breakneck speed. Galaxies don't trickle into existence, they emerge violently. Clumps of stars collide, merge, and grow. Proto-galaxies form chains, clusters, and the earliest shapes we can detect. Some spiral, some ellipticals, some chaotic, irregular blobs. Time in these early regions is compressed. Events that today might take billions of years happen in mere millions. The universe is a fast-forwarded film of creation. Even black holes appear early. Seeds of supermassive black holes form in these dense regions. They devour gas and stars, shaping the evolution of galaxies around them. The cosmic web, the vast network of filaments connecting galaxies, forms rapidly. Dark matter halos provide scaffolding. Baryonic matter, the stuff we see, follows these invisible skeletons. The first galaxies are small, but they grow quickly. Mergers are frequent. Collisions are normal. Violence and chaos dominate the young universe. And yet, from this frenzy, order begins to emerge. Clusters of galaxies form. Cosmic filaments stretch across space. Patterns appear. Structure arises. We see this accelerated evolution in light that has traveled billions of years to reach us. Telescopes reveal galaxies as they were when the universe was a fraction of its current age. We can witness the sprint of cosmic history. Time dilation stretches this light for us, letting us study events we could never experience firsthand. Astronomers map the distribution of early galaxies. They measure star formation rates, galaxy sizes, and shapes. They detect the fingerprints of the first supernovae. We learn how quickly complexity arises from simplicity, from dense gas to shining stars, from isolated stars to entire galaxies, from random clumps to an intricate cosmic web. Every observation confirms the early universe was hyperactive. The cosmic clock ticked faster. Processes are compressed in both space and time. Formation wasn't slow or patient, it was relentless. And it set the stage for everything that followed. Galaxies like the Milky Way, stars like our Sun, planets, chemistry, life. All was born from that accelerated infancy of the cosmos. Understanding this furious early period gives context to why the universe looks the way it does today. It explains the distribution of galaxies. It explains star populations. It explains the heavy elements that make up planets and us. Imagine this. You and a friend watch a firework explode in the sky. You both see it at the same instant. Simple, right? This is how we experience time every day. We assume there's a universal now. What happens here happens everywhere, in lockstep. But the universe laughs at that idea. Enter relativity. Time is not absolute. It bends, stretches, and warps depending on motion and gravity. Now, stretch your imagination across billions of light years. Galaxies receding at 90% the speed of light? Events there unfold much slower compared to us. A star exploding might appear to us as a slow-motion spectacle. Time itself is dilated, stretched by the universe's expansion. This leads to a mind-bending fact. There is no universal now in the cosmos. Two events happening simultaneously for you, for a distant observer, they could happen years apart. Simultaneity is local, not global. The universe doesn't agree on what counts as happening right now. This shatters our intuitive notions of cause and effect across cosmic scales. Ask, what is the universe doing right now? There is no answer. Now depends on where you are and how you're moving. Think of it like a cosmic mirage. The concept of a single, unified present breaks apart. Observers in different galaxies each have their own version of now. A galaxy a billion light years away is not in sync with us. Its stars live in a different temporal rhythm. Expansion accelerates this effect. As dark energy drives galaxies further apart, time dilation intensifies. Future civilizations will see even stranger effects. Some galaxies might appear almost frozen in time. A distant supernova could appear to linger for centuries. Acceleration stretches the universe and stretches time along with it. Simultaneity becomes a cosmic illusion. This has real consequences for understanding the universe. Cosmic events cannot be compared globally. Astronomers must account for this when measuring distances, ages, and velocities. Even the age of the universe becomes relative. From Earth, it's 13.8 billion years. From a galaxy racing away at near light speed, it could look much younger. Time and space are entwined in a cosmic dance. Expansion doesn't just move galaxies apart, it rewrites the rules of time itself. Past, present, and future are observer-dependent. This challenges our common sense. Our intuition is built for a small, local, human-scale universe. On cosmic scales, intuition fails. The universe does not keep a single clock. Every location has its own tick. Every motion affects that tick. The faster a galaxy recedes, the slower its clock appears to us. This has implications beyond science. It changes how we understand history, causality, and cosmic evolution. It reminds us that our perspective is just one among countless others. The universe is vast, expanding, and radically relative. There is no master timeline, no universal snapshot of events. Everything unfolds in a web of relative nows. And yet, from this tangled tapestry, we can still reconstruct cosmic history. We measure redshifts, distances, and motions to piece together a coherent story. But we never escape the reality. Time is personal, local, and in flux across the cosmos. Imagine you're on a cosmic roller coaster. The track is space itself, stretching beneath you, and suddenly, the ride starts speeding up. This is what dark energy does. Dark energy is the invisible force pushing the universe apart. It's subtle, yet relentless. For billions of years, it's been quietly accelerating expansion. Galaxies aren't just drifting away, they're racing into the void. And as they move faster, something astonishing happens. Time itself stretches along with space. Events in distant galaxies appear slower. A star's life could seem stretched over centuries instead of millions of years. The faster a galaxy recedes, the slower its clock appears to us. This is cosmic acceleration in action. It's not just about distance. It's about how time unfolds across the universe. Dark energy's strength grows over time. The farther apart galaxies get, the more powerful the stretching. Expansion doesn't cost, it speeds up, dragging time with it. In about 5 billion years, dark energy began dominating. Before that, gravity slowed expansion. The universe almost collapsed under its own weight. But dark energy changed the rules. Acceleration won. Distances increased faster than gravity could slow them down. The cosmic horizon, the edge of what we can see, starts shrinking. Galaxies disappear from view, not destroyed, just racing beyond our reach. This creates a future universe that is lonely, sparse, and dark. We call this the far future island universe. Only our local group, Milky Way, Andromeda, and their satellites remains visible. Everything else fades into eternal darkness. Time dilation intensifies as well. The more space stretches, the slower events appear to unfold out there. Some galaxies will seem frozen in slow motion. Imagine watching a cosmic clock tick 1 second over a millennium. This isn't science fiction, it's real physics. Dark energy ensures that acceleration grows stronger. If it continues, the universe will never stop expanding. Distances will increase exponentially. Time stretching will reach unimaginable extremes. Events far away may never be completed from our perspective. Stars in distant galaxies may burn out unseen. Galaxies may merge or collapse, but we will never witness it. Even light itself struggles to keep up. Eventually, photons from the edge of the observable universe won't reach us at all. Dark energy is like a cosmic puppeteer. It tugs on space, time, and the fabric of reality itself. And its influence grows as the universe grows. But what about the implications for life and information? Acceleration isolates regions of the universe. Signals, messages, even cosmic histories may become forever unreachable. The farther away an event, the less chance we have to observe it. Knowledge is confined by expansion. Our cosmic perspective shrinks even as the universe grows, yet acceleration also reveals a profound truth. It tells us that the universe is alive with dynamics we barely comprehend. Time, space, matter, energy, they're all linked in this accelerating dance. We witness the universe not as a static backdrop, but as an evolving, expanding stage. And on this stage, dark energy is the director. It decides how fast galaxies recede, how time dilates, and how the future unfolds. Acceleration is not subtle. It shapes the destiny of everything. Stars, galaxies, black holes, and even potential observers. The universe is stretching, accelerating, and rewriting its own clock. Understanding this acceleration is key to predicting the cosmic future. Will it lead to heat death, or something even stranger, like a big rip? Either way, dark energy is the engine driving the journey. And the longer we observe, the clearer the picture becomes. The universe is not coasting, it is racing, and time itself is running along for the ride. Picture this. You're staring at a galaxy billions of light years away. At first, it's bustling stars forming, exploding, black holes feeding. Then, as you keep watching, something strange happens. Time slows down. Not a little. Not like waiting in line, it slows dramatically. This is cosmic time dilation in action. The faster a galaxy recedes due to expansion, the slower its events appear. A star exploding might take centuries instead of seconds. Planets orbiting distant suns seem to crawl along. Even the formation of galaxies stretches over millennia. This isn't imagination. It's the universe's own clock bending. Light itself carries the record of this stretching. Redshift tells the tale. The farther the light travels, the more it's stretched. The wavelengths elongate. The clock behind that light slows. A galaxy at the edge of our observable universe is almost frozen. Its stars, its chaos, its life almost paused. From our vantage point, it's as if time itself has stopped out there. The universe is revealing a hidden truth. Time is relative. Your moment is not universal. A supernova that lasts days in our neighborhood may last centuries for a distant observer, or appear to freeze entirely to us. This extreme dilation happens because space itself is expanding, not just between galaxies, but affecting the very flow of time tied to them. Imagine standing still while the floor beneath you stretches faster and faster. That's what distant galaxies experience relative to us. Their history stretches out like taffy, a billion years of evolution compressed into what we perceive as a heartbeat or frozen snapshot. And it grows more extreme with distance. Galaxies beyond a certain point fade into stillness. Light from them arrives so stretched that every event seems eternal. The first stars, the earliest black holes, everything appears paused. We are witnessing time itself unraveling at cosmic scales. Dark energy is the accelerator behind this phenomenon. It drives galaxies apart faster, amplifying the slowing effect. Every second we observe them, the universe is stretching its moments beyond comprehension. Eventually, some events are forever unreachable. Even photons from the farthest galaxies cannot bridge the growing gap. They are trapped beyond the cosmic horizon. From our perspective, they are lost to eternity, frozen in a distant past. This gives a surreal view of the universe. Active, chaotic nearby galaxies. Frozen, almost eternal, distant galaxies. It's a cosmic stage where time moves unevenly. The more the universe expands, the more pronounced the freezing. Future civilizations will see an even darker picture. Many galaxies will have vanished beyond visibility. Light from the distant past, once a guide to cosmic history, will be gone. Only the local cosmic neighborhood remains active and observable. Extreme time dilation is a window into the universe's hidden dynamics. It reveals the influence of dark energy, the flow of cosmic time, and the limits of observation. We see that the universe is not uniform in experience. Nearby events happen fast. Distant events nearly stand still. The cosmos is a patchwork of temporal speeds. This perspective reshapes our understanding of evolution, history, and observation. We realize the universe is not just vast in space, but in time itself. Every distant galaxy is a frozen monument to the early cosmos. And through time dilation, we glimpse the profound effects of expansion on reality itself. The universe stretches not just space, but time, memory, and observation. Imagine the universe billions, trillions, even quadrillions of years from now. Stars are gone. Galaxies are faded whispers. Black holes, the last titans, slowly evaporate. The universe reaches perfect stillness. This is the heat-death scenario. A future so distant, it almost defies imagination. Heat death isn't fiery, it's cold. It's not chaos, it's absolute equilibrium. Every particle has settled. Energy is evenly spread. Nothing moves without purpose. No stars ignite. No planets orbit. No chemistry occurs. Even black holes, once enormous engines of cosmic destruction, vanish through Hawking radiation. The universe becomes a silent void. Space itself continues expanding, but it carries only emptiness. Temperature approaches absolute zero. Nothing can happen. No energy gradients exist to drive processes. No new stars, no new life, no new civilizations. Time continues, but nothing evolves. Matter itself doesn't last forever. Protons may decay, leaving only electrons, positrons, and photons. Atoms, planets, galaxies, all fade into fundamental simplicity. Everywhere you look, the universe is uniform and empty. It's the ultimate victory of entropy. Every system that could dissipate energy has done so. Every process that could occur has ended. All that remains is cold radiation and scattered particles. It's a universe stripped of structure, stripped of complexity. No observers remain to measure it. No one remains to witness the end of cosmic history. Even memory, even information, has no home. Time itself might continue, but the universe is static in effect. Expansion carries this empty cosmos further outward. Even light struggles to reach across the void. The cosmic microwave background, the faint whisper of the Big Bang, is now undetectable. All evidence of the universe's origin is lost. For any observer, the universe appears eternal and unchanging. This is heat death, the silent, inevitable end of all energy-driven phenomena. It's not violent. It's inescapable. It's the slow, quiet extinguishing of cosmic activity. From our current perspective, it's almost impossible to grasp. Trillions of years pass like fleeting moments. Stars live their lives, galaxies dance and collide, black holes form and evaporate, and still, entropy marches on. Every form of energy spreads thinner and thinner. The universe approaches the maximum entropy state. This fate arises from the fundamental laws of thermodynamics. Energy cannot disappear, but energy can disperse. And when it disperses evenly, nothing can happen. The cosmos reaches perfect balance. It's the ultimate cosmic irony. From the Big Bang's fiery, dense chaos, to a vast, cold, lifeless expanse. All complexity, all structure, all drama gone. Yet, this scenario depends on current physics holding true. Dark energy must persist. Expansion must continue. If something changes, new physics, new forces, new phenomena, the end could be different. But under our current understanding, heat death is the unavoidable final act. A universe without stars, without galaxies, without movement. A universe in eternal silence. And in that silence, we can see a mirror of life itself. Everything that rises will eventually fade. Every story, every structure, every spark of energy has a lifespan. The universe teaches patience and humility, because even on the grandest scales, entropy rules all. Imagine a universe where the last bright stars have flickered and died, where light itself has grown scarce. This is the degenerate era, a time when the cosmos is no longer vibrant, but quiet. Galaxies exist, but they are dark skeletons of their former selves. No new stars are forming. The gas needed for star formation is too thin, too spread out. Gravity can no longer gather enough material to ignite fusion. The universe has entered a phase of slow decay. Stars that remain are remnants, white dwarfs, neutron stars, black holes. White dwarfs, small dense cores of dead stars, glow faintly. They burn not with fusion, but with residual heat. Over trillions of years, even this energy fades. Neutron stars, remnants of massive stars that went supernova, drift silently through space. They are ultra-dense, powerful, but invisible to casual observation. Black holes continue their slow, inexorable evaporation via Hawking radiation. They are the final engines of energy in the universe. As time stretches on, even these remnants will fade. Stars no longer light up the cosmos. Planets orbit cold, dead cores. Molecular clouds, once nurseries for new stars, vanish. The universe is no longer a place of creation. It is a museum of decay. Everything that once blazed with life and energy now exists in silent stillness. Galaxies drift apart as expansion continues. Some collide, forming quiet, dark giants, but even these mergers produce no new energy. The degenerate era is dominated by cold, dense remnants. White dwarfs slowly cool toward black dwarf status. Dark, cold, invisible. Neutron stars wander endlessly, remnants of violent pasts, yet powerless to create anew. Black holes shrink imperceptibly, releasing tiny amounts of energy over unfathomable timescales. The universe's temperature drops closer to absolute zero. Energy is spread so thin that motion and interactions are minimal. Time continues, but the universe is static in effect. The cosmological landscape is sparse. Even light has fewer places to travel. The universe is almost empty. Yet, this era is not eternal. Even degenerate remnants are not immortal. Protons may decay, matter itself may break down into fundamental particles. Eventually, all structure disappears. But for now, the degenerate era is a long period of cosmic quietude. It follows the death of stars, the cessation of fusion, the end of galactic fireworks. It is a transitional phase between the vibrant past of stars and galaxies and the ultimate fate of the universe. For civilizations that survive into this era, the night sky would appear empty. No twinkling stars, no glowing galaxies. Only darkness, punctuated by the rare flash of a black hole evaporating. This era is unimaginably long. Trillions upon trillions of years pass with minimal activity. Time itself becomes a measure of decay, not creation. Yet, it is a fascinating period for cosmologists. The degenerate era reveals the impermanence of stars, the fragility of galaxies, the ultimate limits of matter. It's a reminder that the universe evolves on scales far beyond human comprehension. No explosions, no collisions, no fusion, just slow, inevitable decline. Eventually, even this era will end. White dwarfs will cool. Neutron stars may decay. Black holes will evaporate. The cosmos will edge closer to heat death, a silent and empty universe. For now, the degenerate era is the last act of cosmic remnants, the quiet aftermath of the universe's once vibrant youth. Time stretches endlessly, the stage is dark, and the cosmos waits for the final chapter. Imagine a universe so old that even atoms, the building blocks of everything, begin to vanish. Welcome to the era of proton decay. It's a time beyond comprehension. Beyond stars, beyond galaxies, beyond anything familiar. In this era, the very matter that makes up planets, stars, and even us begins to disintegrate. Protons, the stable cores of atoms, are not eternal. Theoretical physics predicts that after roughly 1034 years, protons may decay. One by one, they break down into lighter particles, positrons, neutrinos, photons. Atoms crumble, molecules dissolve, planets lose their structure. Stars are no longer held together by atomic matter. Everything familiar, the periodic table, the molecules of life, even the dust between stars, ceases to exist. The universe is reduced to a sparse soup of fundamental particles. No complexity remains. No chemistry, no biology, no planets. Matter, as we know it, is gone. Even black holes, though still massive, are left in a universe mostly devoid of ordinary matter. Proton decay is a slow process, not something we could observe directly. Trillions of years stretch between events. Yet, the outcome is inevitable if current physical laws hold true. Imagine the Earth. Its atoms slowly vanish. The ground beneath your feet gone. Oceans dissolved. Even you no longer composed of stable particles. The universe becomes an empty, diffuse void, sprinkled with the occasional black hole or decayed particle. Time stretches on. Even this sparse particle soup eventually thins as expansion continues. Distances between remaining particles grow vast, nearly infinite. Energy is spread across an ever-expanding cosmos. The universe is cold. Absolute zero is approached. Nothing new can form, no reactions, no motion of matter in any meaningful sense. This is the quiet aftermath of the degenerate era, the ultimate stage of matter breakdown. From vibrant galaxies to lonely black holes, and now to atomic dissolution, the universe has entered a phase of perfect entropy. All potential for new structure is gone. Yet, even in this bleak picture, physics still hums at the smallest scales. Virtual particles continue to flicker in and out of existence. Quantum fluctuations persist, subtle and imperceptible, in the background of the decayed cosmos. But these tiny sparks cannot recreate matter as we know it. Atoms, the framework of reality, are gone. The universe is a memory of its past self. All that was once solid, tangible, and alive has faded. Proton decay teaches us the impermanence of even the most fundamental components of reality. Nothing lasts forever. Not stars, not planets, not atoms. Everything obeys the laws of entropy and time. And yet, in understanding proton decay, we gain a profound perspective on existence. It reminds us that life and structure are temporary, beautiful flashes in an ever-aging cosmos. So, as we continue our journey through cosmic evolution, remember this: even the atoms in your body are part of an impermanent universe. One day, they too will dissolve, leaving only a sparse, cold universe behind. But for now, we are here. We exist, and we can witness, learn, and marvel at the universe's grand story. Stay curious, keep exploring, and if you want to continue this journey through cosmic time and witness the ultimate fate of everything, hit that subscribe button now, because the story of the universe is far from over. Welcome to the black hole era, a time when stars are long gone, galaxies are dim, even ordinary matter has largely disintegrated. All that remains are black holes, lonely titans lurking in the dark. Imagine the universe as a vast, empty stage. The only actors left? Black holes of all sizes, from small stellar remnants to gargantuan supermassive giants that once ruled the hearts of galaxies. These black holes are not static. They're slowly evaporating through a process called Hawking radiation. Particles leak from the event horizon. Energy escapes. Mass shrinks. It's a gradual process, imperceptible on human timescales. Stellar mass black holes will persist for trillions of years. Supermassive black holes, like those at galaxy centers, linger even longer, up to 100 years. The universe has become a dark, lonely realm of fading giants. No new stars form. No new matter accumulates. The cosmic expansion continues, stretching what little energy remains. Even the energy from evaporating black holes spreads thin across a growing void. Black holes are the last sources of observable energy in this vast emptiness. They dominate the cosmic landscape. Their Hawking radiation is the universe's final glow. It's faint, it's ephemeral, but it's still there. Slowly, imperceptibly, the universe empties. Eventually, the last black hole evaporates. All that remains is perfect emptiness. No matter, no stars, no galaxies, only a diffuse sea of photons, neutrinos, and other elementary particles drifting across an infinite void. Time marches on. Expansion stretches this sparse energy across ever-increasing space. The universe is cold. Absolute zero is approached. All processes capable of generating work, chemical, nuclear, gravitational, have ceased. Even the subtle dance of quantum particles continues only in isolation, unable to form structures. The black hole era teaches us a profound truth. Even the universe's most massive objects are temporary. Even the giants that once dominated galaxies will fade into nothingness. The cosmos is a story of impermanence. Every object, no matter how massive, is subject to the laws of entropy. Yet, in this emptiness, there's a certain cosmic poetry. The universe has transitioned from vibrant complexity to elegant simplicity, from bustling galaxies to solitary black holes, to a universe almost devoid of matter. It's the ultimate endgame of cosmic evolution, an era defined by slow decay and fading energy. And it raises questions about the meaning of time and existence itself. What is left when the universe's most massive structures vanish? What remains when all that once existed is reduced to isolated particles in empty space? These questions echo through the vast black hole era, and yet they are part of the universe's story. A story that began with the Big Bang, saw stars and galaxies form, witnessed life emerge, and now reaches the slow, quiet dominance of black holes. But remember, even in this darkness, there is a lesson. All things are temporary. Everything fades. And yet, understanding this fading is part of our cosmic journey. So keep asking, keep learning, and keep exploring. Because the universe is far bigger, stranger, and more beautiful than we can imagine. And the story doesn't end here. Welcome to the final heat death, the ultimate fate of the universe. A time so distant, it defies comprehension. The cosmos has passed the black hole era. Even the last black holes have evaporated. No stars remain, no galaxies, no planets, no matter as we know it. Only a thin sea of elementary particles, photons, neutrinos, electrons, drifting across an infinite void. Energy is spread so thin that no process can occur. No chemical reactions, no nuclear fusion, no gravitational interactions strong enough to form structures. Time continues, but nothing meaningful happens. This is maximum entropy, a universe in perfect equilibrium, every corner of space at the same temperature. No gradients exist. No work can be done. No energy differences remain. The universe has reached thermodynamic death. All activity is gone. All change has ceased. The cosmos is silent, cold, unchanging. Even light is stretched by expansion to undetectable wavelengths. The observable universe has vanished. Any future observers, if they could exist, would find a universe that appears eternal, static, and lifeless. No evidence of the Big Bang, no trace of galaxies, no hints of stars that once burned brightly. The history of the cosmos is erased by time and expansion. This is the ultimate consequence of cosmic expansion and dark energy. The universe will persist forever, but in a state of absolute emptiness. It is a final, silent monument to entropy. Yet, even in this emptiness, there is a profound lesson. The universe is finite in its activity, but infinite in its time. Every star, every planet, every particle, every life form, even galaxies themselves were fleeting actors on a stage that will last forever. All complexity, all structure, all energy eventually succumb to the laws of physics. Heat death is not violent. It is inevitable, gradual, quiet, a universe without events, without processes, without change. A cosmos stripped of everything that makes it dynamic and alive. Yet, in understanding this fate, we gain perspective. We see the fleeting nature of our existence. We see the preciousness of structure, of life, of stars, of galaxies. We see how expansion and entropy shape everything. Even the most massive objects are temporary. Even black holes evaporate. Even the energy of the universe is eventually spread thin. The universe's story is ephemeral, yet magnificent. Heat death marks the end of all activity, but not the end of understanding. By studying cosmic evolution, we glimpse the full timeline from the Big Bang to the final heat death. We see how the universe creates, evolves, and eventually dissolves. It's a timeline spanning trillions upon trillions of years, far beyond human comprehension. And yet, every moment we live occurs in the midst of this grand story. We are part of a universe that grows, changes, and ultimately fades. Heat death is the inevitable conclusion of everything, the final chapter in the cosmic saga. No matter, no light, no processes remain. Maximum entropy, infinite time, a cold, dark, silent expanse. Yet even in this ultimate emptiness, the universe exists. It is a universe without action, but not without presence. A monument to the laws of physics, a reminder of the beauty of impermanence. And it challenges us. If the universe fades to nothingness, how do we define meaning in the time we do have? So look up, cherish the stars while they shine, appreciate the galaxies while they exist, because even in a universe destined for final heat death, the story we witness today is extraordinary. Imagine looking up at the night sky billions of years from now. What do you see? Only your local group of galaxies, the Milky Way, Andromeda, their tiny satellite galaxies. The rest? Gone. Distant galaxies have vanished beyond the cosmic horizon. They haven't been destroyed. They haven't disappeared. They've simply receded faster than their light can reach us. Dark energy drives this relentless expansion, and as space stretches, light from these faraway galaxies becomes increasingly redshifted. Eventually, the wavelengths stretch so long that no instrument, no telescope, no detector can see them. They fade into invisible oblivion. For future astronomers, the universe will look empty. No galaxies racing away. No Hubble expansion. No cosmic microwave background. Just a few islands of stars floating in a vast void. It's a universe stripped of its cosmic perspective. The evidence that revealed the universe's true nature today will be gone. The clues that led us to understand the Big Bang redshift patterns, distant galaxies, the cosmic microwave background will be lost forever. Future civilizations will observe a small, isolated universe and conclude it is static and eternal. They will see no expansion, no history, no evolution. The cosmic horizon creates a boundary we cannot cross. Everything beyond it is permanently unreachable. It's not science fiction. It's a natural consequence of accelerating expansion. In today's universe, light from billions of galaxies reaches us, giving a full picture. In the far future, light from all but our local group fails to arrive. The horizon is shrinking in terms of observable galaxies. Even if civilizations invent technology beyond our imagination, these galaxies are forever lost to view. This has profound implications. Science relies on observation. Without light from distant galaxies, how do future astronomers reconstruct cosmic history? They will lack the clues that allowed us to see the universe as expanding. They might never know the universe had a beginning. They might think the cosmos has always been the same. The cosmic horizon isolates observers. Every civilization is trapped within its own bubble of visible galaxies. Distances that were once measurable become meaningless. Hubble's law, the very principle showing universal expansion, cannot be tested. The story of cosmic evolution fades. Only local matter remains accessible. Our solar system, our galaxy, a few neighboring galaxies, these become the entire observable universe. This is the ultimate fate of cosmic perspective. Information about the universe beyond the horizon is lost for all eternity. Even if the universe is infinite, observers cannot know it. The cosmic horizon doesn't destroy galaxies. It erases their accessibility. Light can't traverse the ever-expanding space. Signals can't reach across the growing gulf. Every distant star, every distant galaxy, every distant supernova fades into permanent darkness. The universe becomes locally finite, even if globally infinite. And in this isolation, future astronomers may misinterpret the universe. They might conclude it is smaller, simpler, and unchanging. The truth of billions of years of cosmic history will be hidden beyond the horizon. It's a chilling reminder. Expansion doesn't just shape the universe. It shapes what can be known. The cosmic horizon limits knowledge, observation, and understanding. It divides the universe into observable islands. And all this happens quietly, slowly, inexorably. Space stretches, galaxies vanish. The universe grows emptier. Observers are left with islands of stars in a dark sea. Picture a future civilization, billions of years from now. They peer into the night sky. What do they see? A few dozen galaxies at most. Their own Milky Way, Andromeda, maybe a few satellites. The vast majority of the cosmos? Gone. Not destroyed, not absent, simply beyond reach. Dark energy has carried those distant galaxies beyond the cosmic horizon. Their light can never reach these observers. The red-shifted signals fade into invisibility. No cosmic microwave background. No distant galaxies racing away. No trace of the universe's fiery birth. The universe appears small, quiet, and static. For these astronomers, the cosmos seems eternal, unchanging, immutable. Their telescopes, no matter how advanced, cannot detect what lies beyond their local galactic neighborhood. It's as if the universe has shrunk to the size of a single island. The evidence we take for granted today, the very clues that revealed expansion and the Big Bang, will be completely lost. Without distant galaxies, they cannot discover Hubble's law. Without the cosmic microwave background, they cannot infer a hot, dense origin. They might conclude the universe has always existed this way. The richness of cosmic history becomes inaccessible. Science relies on observation, on evidence. But the accelerated expansion isolates observers, creating a natural limitation. Everything outside their cosmic horizon is unknowable. Light from faraway stars, supernovae, and galaxies simply cannot arrive. Future astronomers will be like sailors in a vast ocean, stranded on a single island. No matter how powerful their instruments, the rest of the world is unreachable. The universe becomes locally finite, a small neighborhood masquerading as the entirety of existence. Even if the cosmos contains billions of galaxies, these observers will never see them. This creates a profound epistemological problem. How do you understand something when most of it is forever invisible? They might measure the distances of their local galaxies, observe stellar motions, and chart gravity within their limited region. But the big picture expansion, cosmic evolution, the fate of the universe is gone. The universe appears static because all evidence of change has vanished. Future civilizations could reconstruct some aspects of physics, but the history of cosmic expansion. Lost, the story of billions of years of growth, collisions, mergers, and evolution fades. Even light from early stars and galaxies that once illuminated the cosmos is now beyond reach. Observational evidence that allowed us to piece together the Big Bang will be invisible. They may even develop cosmological theories, but their conclusions will be incomplete or misleading. The universe, once dynamic and vast, becomes a small, quiet laboratory. A handful of galaxies floating in an eternal void, no Hubble expansion to measure, no distant supernovae to map, no ancient radiation to reveal origins, just local matter in a silent cosmic neighborhood. The lesson is stark. Cosmic expansion doesn't just move galaxies apart, it erases knowledge. It limits what can be observed, understood, and remembered. The universe itself sets the boundaries of comprehension. Future astronomers will live in a universe that appears simple, static, and eternal, but the reality beyond their horizon remains vast, dynamic, and unknowable, and all of it vanished from view simply because space keeps growing. Imagine a universe on the edge of chaos, a place where the very fabric of reality is under siege. Dark energy, the mysterious force driving cosmic acceleration, grows stronger over time, not just a gentle push, but an ever-intensifying shove. At first, the effects are subtle. Galaxies drift apart slightly faster than before. Clusters of stars feel the pull weakening. But as dark energy strengthens, the consequences become catastrophic. This is the scenario physicists call the Big Rip. It's a universe where expansion doesn't just separate galaxies, it tears everything apart. Billions of years before the final end, galaxy clusters begin to dissolve. Gravity can no longer hold them together. Galaxies themselves start drifting apart, their stars racing into the growing void. Eventually, even individual galaxies cannot resist the pull. Their stars scatter. The Milky Way, once a tightly bound spiral of billions of suns, fragments. Stars float alone in an ever-expanding emptiness. Dark energy's strength continues to climb. Next, the very fabric of solar systems comes under attack. Planets are torn from their orbits. Moons drift away. Gravity becomes powerless against the relentless expansion of space. Even atoms are not safe. Molecular bonds, the glue holding matter together, begin to fail. Water molecules stretch apart. Solids cannot maintain structure, and in the final moments, the strong nuclear force, which binds protons and neutrons in atomic nuclei, gives way. Matter, as we know it, ceases to exist. Every particle, every atom, every building block of stars, planets, and life is shredded. Space itself stretches so violently that distance becomes meaningless. Time itself may break down under these conditions. The Big Rip is the ultimate cosmic disassembly. No star, no planet, no galaxy, no life survives. It's a universe where the laws of physics are overpowered by the sheer expansion of space. The timeline of this apocalypse depends on how quickly dark energy strengthens. Conservative estimates place the Big Rip about 22 billion years from now. Some more aggressive models suggest it could occur sooner, within a few billion years. For any civilization witnessing it, the universe would appear to dissolve piece by piece. First, distant galaxies disappear from view, then clusters, then galaxies themselves. Solar systems unravel, planets float alone in space. Finally, atoms themselves are unmade. The Big Rip is not slow and gentle like heat death. It is sudden, violent, and absolute. It contrasts sharply with the steady, quiet fading of stars into darkness. Where heat death stretches over unimaginable trillions of years, the Big Rip tears the cosmos apart in a cosmic crescendo. This scenario depends entirely on the behavior of dark energy. If it remains constant, a Big Rip never happens. The universe expands forever, but remains intact, slowly approaching heat death. But if dark energy strengthens, the Big Rip becomes inevitable. It is a terrifying glimpse of what could occur if the forces shaping the cosmos shift beyond our expectations. It reminds us that the universe is not a static backdrop. It is alive with forces, energies, and possibilities that can destroy reality itself. Even our most fundamental assumptions, gravity, atomic cohesion, causality, can be challenged by cosmic expansion. The Big Rip is a stark warning. In a universe governed by accelerating expansion, nothing is guaranteed to endure. Look around you. Everything seems solid, stable, familiar. Even the emptiest space feels like nothing. But nothing is a lie. Empty space is far from empty. It's a seething, restless ocean of energy, bubbling with activity at scales too small to see. Physicists call it quantum foam. At the tiniest scales of reality, smaller than an atom, smaller than a nucleus, the vacuum is alive. Particles appear and vanish in flashes of existence. Electron-positron pairs spring into being, only to annihilate each other almost instantly. Heavier particles flicker even faster. These are the virtual particles of quantum mechanics. They are invisible, ephemeral, yet their effects are real. They push and pull, they shape forces, they create measurable phenomena. One example, the Casimir effect. Two metal plates, placed extremely close in a vacuum, experience a force pushing them together. No air, no matter, just the quantum vacuum itself. These virtual particles are excluded between the plates, creating a pressure imbalance. You can literally feel the weight of empty space. Now, imagine this energy stretched across the universe. Each cubic centimeter of vacuum contains energy, small but cumulative. Physicists tried to calculate this energy. They expected enormous numbers, 10, 120 times larger than what we observe. This is the vacuum catastrophe, the greatest mismatch in theoretical physics. Either our understanding of quantum mechanics is incomplete, or some unknown mechanism suppresses most of this energy. And yet, some residual vacuum energy persists. It could be the mysterious dark energy accelerating the universe's expansion. Every flicker, every virtual particle might contribute to the stretching of space itself. But quantum foam does more than push space outward. At the Planck scale, 10, 35 meters, space itself is turbulent. It's grainy, chaotic, frothing with appearing and disappearing geometry. Distances lose meaning. Time blurs. The universe at this scale is not smooth. It's a storm of possibilities. Some theories suggest that this vacuum energy is a clue to unifying quantum mechanics and gravity. Maybe the secret of cosmic expansion, dark energy, and the Big Rip all reside in the quantum froth. String theory imagines space emerging from tiny vibrating strings. Loop quantum gravity envisions space as discrete atoms linked like a cosmic crystal. Either way, the vacuum is structured, alive, anything but empty. And here's the paradox. This restless vacuum underpins all cosmic stability and chaos. It drives expansion. It seeds energy. It defines what space can do. Every flicker might ripple across time and space, leaving subtle traces in the cosmos. This invisible, turbulent sea is the stage for everything we see. Galaxies, stars, planets, life, they all emerge from and exist within this energetic foundation. Yet we rarely think about it. We look at the night sky and see emptiness, but that emptiness is the engine of the universe, the playground where reality itself is constantly remade. Quantum foam reminds us that the universe is not a passive container. It's a dynamic, ever-changing arena where energy and space are intertwined, and where the tiniest flicker can have cosmic consequences. Next time you think of nothing, remember, the vacuum is a storm of creation, a restless playground fueling cosmic evolution, expansion, and the very possibility of existence itself. You think you know particles, electrons, protons, neutrons, stable, predictable, measurable. But the universe has a secret, a hidden population of particles that exist without existing. Physicists call them virtual particles. They are the ghosts of the quantum world. They pop into existence, just for a fraction of a second, then they vanish. No mass, no trace, yet they exert influence on everything around them. Sound impossible? It's quantum mechanics. These particles obey the uncertainty principle. They borrow energy from the vacuum. They must pay it back almost instantly. Electron-positron pairs flash into being, then collide and annihilate. Heavier pairs flicker and disappear even faster. The universe at this scale is like a busy street, full of invisible pedestrians we cannot see, but whose footsteps we feel. One of the clearest demonstrations of their existence is the Casimir effect. Place two uncharged metal plates extremely close together. No air, no liquid, no visible particles between them. Yet the plates experience a measurable force pushing them together. Virtual particles outside the plates crowd the vacuum, while the space between them is depleted. This imbalance exerts real pressure. You are literally feeling the influence of particles that don't exist in the usual sense. Virtual particles also shape atomic energy levels. The famous Lamb shift shows that even the energy of a hydrogen atom is subtly altered by the presence of these quantum ghosts, and they play a role in fundamental forces. The photon, the carrier of electromagnetic force, itself interacts with a swarm of virtual particles. Gravity, though weak, might be influenced by similar quantum froth at tiny scales. Now consider the universe on a cosmic scale. Every cubic centimeter of empty space is teeming with virtual particles. This sea of phantom energy contributes to the vacuum energy that drives cosmic expansion. It may be the dark energy we detect pushing galaxies apart. Even the largest structures, clusters of galaxies, cosmic filaments, owe part of their evolution to these fleeting entities. And here's a twist. These particles aren't just fleeting annoyances. They encode the rules of reality. They dictate how forces act, how energy flows, how space behaves. Without virtual particles, the universe as we know it would collapse into chaos or never exist at all. Yet we never see them directly. Our instruments detect only their effects. They are a reminder that observation is limited. The universe is more than what meets the eye. It hides complexity in every corner, every moment, every fraction of a second. Virtual particles are the heartbeat of empty space, unseen but undeniable. They bridge the microscopic world of quantum mechanics and the cosmic dance of space and time. They are proof that nothing is never nothing. Even in the vastest vacuum, something stirs. Something that shapes reality, governs cosmic expansion, and whispers the secrets of existence. Next time you think about emptiness, remember, the vacuum is alive. Virtual particles are its dancers, fleeting yet potent. Every flicker, every collision, every ghostly appearance writes the story of the universe, from the tiniest atom to the farthest galaxy. Don't blink. You might miss the most important actors in the cosmic play. Empty space isn't empty. You've heard it before, but now it gets real. In a lab, physicists have measured the vacuum's invisible power. This is called the Casimir effect. Imagine two metal plates, tiny, smooth, parallel, placed extremely close together, less than 1,000th of a millimeter. You'd think nothing would happen. No air, no particles. Yet the plates move toward each other. No hands, no magnets, no magic. Just empty space doing its thing. How is this possible? It's the universe at work, on a scale too small for our eyes. Virtual particles, those fleeting quantum ghosts, are everywhere. They pop in and out of existence in the vacuum. Outside the plates, they swarm freely. Inside, the space is squeezed. Fewer quantum fluctuations can fit. This imbalance creates a pressure pushing the plates together, a force from nothing. It's tiny, but measurable and undeniable. Physicists have repeated the experiment with incredible precision. The results always match predictions. Empty space isn't passive. It's alive with quantum activity. The Casimir effect proves it. It shows that nothing can have effects you can measure, you can touch indirectly, of course. Now, think bigger. If empty space has measurable effects in a lab, what about on a cosmic scale? Every cubic centimeter of the universe is full of this quantum energy. It contributes to dark energy, the mysterious force accelerating cosmic expansion. The same physics that pushes the Casimir plates together might be pushing galaxies apart. Tiny laboratory experiments connect directly to the fate of the universe. It's a bridge between quantum mechanics and cosmology, and it's profoundly counterintuitive. We trust that empty space means nothing, but the Casimir effect says, not so fast. Look closer. Even when stripped of matter, energy, and light, space itself has structure, energy, and power. The effect has practical implications too. Nanotechnology engineers must account for Casimir forces. Micromachines can stick together unexpectedly because of vacuum pressure. This isn't science fiction. It's physics at work in the lab and in the universe. It's the universe whispering its rules in every corner of reality. Even the simplest experiment teaches profound truths. Nothing is never nothing. The vacuum is a seething playground of possibilities. Every flicker of a virtual particle contributes to the invisible scaffolding of reality. Casimir made this real. He turned theory into measurable proof. The plates don't lie. Empty space has tangible effects, shaping the way matter behaves at the tiniest scales. And through these tiny forces, we glimpse the universe's hidden energy, the same energy that might drive cosmic acceleration, the same energy that shapes the ultimate fate of galaxies, stars, and perhaps even life itself. Next time you think about nothing, remember, even nothing pushes, pulls, and defines everything. The Casimir effect is the laboratory echo of the universe's deepest secret. It's proof that reality does not require matter to matter. And it's a reminder. Sometimes, the most profound truths are found in the quietest places, the space between the things we can see. Empty space holds a secret. Not just Casimir forces or quantum fluctuations. Something much bigger. Something that shakes the foundation of physics. This is called the vacuum catastrophe. Let's start with quantum mechanics. It tells us that empty space isn't empty. It teems with virtual particles. They pop in and out of existence, constantly, everywhere, even when nothing else is around. Now, Einstein's cosmological constant enters the scene. He imagined that empty space could have energy, repulsive energy, a gentle push that could affect the universe itself. Fast forward to today, we see dark energy driving cosmic acceleration. It's like Einstein's intuition was right. But here's the catch. Quantum mechanics predicts the energy of empty space, and it predicts a ridiculously large number. We're talking 10, 120 times larger than what we observe. Yes, that's not a typo. Imagine, the universe should be tearing itself apart from vacuum energy alone. Galaxies, stars, planets, all obliterated instantly. But clearly, it didn't happen. We're still here. The observed dark energy is tiny in comparison. A whopping discrepancy between theory and observation. This is the vacuum catastrophe. It's not a small error or a rounding mistake. It's a fundamental mismatch. Quantum mechanics tells us one thing, cosmology tells us another, and reality follows cosmology. Clearly, the universe didn't explode from vacuum energy. So, what's going on? Physicists are scratching their heads. Some propose that a cancellation mechanism suppresses most of the vacuum energy. Only a tiny remnant remains to drive cosmic acceleration. Others suggest that our understanding of quantum mechanics, or gravity, is incomplete. We might be missing new physics, hidden rules, things we haven't yet discovered. The vacuum catastrophe also highlights a cosmic coincidence. Dark energy is small, but dominates now. Not billions of years ago, not billions of years in the future now. If it were stronger, the universe would have ripped apart. If it were weaker, galaxies might never have formed. We live at the perfect cosmic moment to notice it. It's both terrifying and awe-inspiring. Tiny, invisible energy shapes the fate of everything. The vacuum catastrophe reminds us that the universe is far stranger than our equations predict. It pushes scientists to question assumptions, to rethink the laws we take for granted, to explore new theories that unify the quantum and the cosmic. It's a puzzle at the intersection of the smallest and the largest scales. From virtual particles to galactic expansion, it connects the microscopic to the cosmic. Some theorists propose dynamic dark energy, a force that changes over time. Maybe it avoids the catastrophe. Maybe it explains the cosmic coincidence. Or maybe the universe is simply fine-tuned in a way we don't yet understand. Whatever the solution, the vacuum catastrophe stands as a reminder of the universe's mystery. It teaches humility. It shows that our understanding is always evolving, that reality often defies expectation, and that even the emptiest space holds secrets capable of reshaping existence itself. So next time you look at the night sky, remember, the vast void between stars is alive with energy. Energy we cannot see. Energy we cannot touch. Energy that might have torn everything apart or shaped everything we know. The vacuum catastrophe is one of the universe's most profound riddles, a tiny number that controls the largest scales, a subtle force that defines our cosmic fate. And it all starts with nothing. Dark energy. The name alone sounds mysterious, and it should, because it's one of the universe's greatest secrets. It's invisible, it's silent, it's everywhere, yet it dominates everything. How can something so elusive control the fate of billions of galaxies? Let's break it down. We already know from observations, the universe isn't just expanding, it's accelerating. Stars, galaxies, clusters, they're all drifting apart faster every moment. This isn't gravity at work. Gravity pulls, dark energy pushes. It's like the universe has a hidden engine, quietly inflating space itself. Now, what is dark energy? The simplest explanation is Einstein's cosmological constant, a tiny energy inherent in empty space. It doesn't clump like matter, it doesn't fade over time, it just exists, uniformly, everywhere, even between galaxies. This constant energy exerts negative pressure, which creates a repulsive gravitational effect. Instead of pulling, it pushes space apart. The effect is subtle locally. We don't notice it in the solar system, but on cosmic scales, it dominates. It controls how galaxies drift apart, how clusters form or fail to form. It defines the ultimate fate of the universe. Here's the kicker. Dark energy is tiny, measured as about 68% of the universe's total energy density. That's huge in cosmic influence, but tiny compared to quantum predictions. Quantum field theory predicts vacuum energy should be 120 orders of magnitude larger than what we observe. And yet, the universe didn't rip itself apart. This is the same puzzle we call the vacuum catastrophe. Dark energy is the survivor, the remnant left after some cosmic balancing act. Why this tiny value? Why now? This is the cosmic coincidence problem. If dark energy had been stronger or weaker in the past, galaxies, stars, and planets might never have formed. Life as we know it would be impossible. Yet here we are, observing the universe just as dark energy becomes dominant. Timing, it seems, matters. Some theorists suggest dark energy is dynamic, not constant, but evolving. It might change strength over billions of years. Some models call this quintessence, a mysterious field slowly filling space. Others stick with the cosmological constant, a simple, timeless energy. Whatever its true nature, dark energy reshapes the cosmic story. It doesn't just affect the present, it rewrites the future. Galaxies we see today, they may drift beyond our reach. Stars forming now, they may be the last. The ultimate destiny, heat death, big rip. or something entirely new is in its hands. Dark energy forces us to confront a strange truth. The universe isn't static. It isn't predictable in the long term. It's alive with expansion. Every cubic meter of empty space contributes to this cosmic push, invisible but powerful. And it raises deep philosophical questions. How much of reality is hidden from us? How can the tiniest vacuum energy govern the largest scales? What else is lurking in the cosmic shadows, shaping the fate of everything we see? Dark energy is proof that emptiness is not nothing. It's energy, it's force. It's the engine of cosmic evolution, and we are witnessing it in action. Every observation, every measurement, every distant supernova dark energy is writing the story. We just have to read it and marvel. Let's talk math. Don't worry, it's not scary. In fact, it's the most powerful lens we have to understand the universe. It's called the scale factor. The scale factor is like a cosmic ruler, a simple number that tells us how big the universe is at any given moment. Right now, by convention, we call it 1. Today's universe, fully expanded, equals 1. What about the past? When the universe was half its current size, scale factor, 0.5. When it was 1,000th its size, scale factor, 0.001. Tiny numbers, big implications. Every galaxy, every star, every atom was closer together, time and space intertwined. The scale factor grows as the universe grows. Double the scale factor, and all distances double. Triple it, and distances triple. It's direct, simple, precise. Now, here's why it matters. Cosmologists use the scale factor to link distance, redshift, and cosmic time. When we look at a galaxy billions of light years away, its light is redshifted, longer wavelengths, stretched by expansion. The scale factor tells us exactly how far the universe has stretched since that light was emitted. A galaxy with redshift 1? The universe was half its size back then. A galaxy with redshift 10? The universe was 1/11th its current size. Every observation becomes a time machine. We see the past, we measure the present, and we predict the future. How? Through equations. Einstein's general relativity provides a framework. Plug in the scale factor, matter, radiation, and dark energy. Out pops the universe's expansion history. Linear growth, constant expansion. Faster than linear? Acceleration. Slower than linear? Deceleration. Observations match acceleration. The scale factor shows dark energy dominance over the last 5 billion years. It tells us how galaxies drift apart faster and faster. It predicts heat death scenarios. Exponential growth leads to near total isolation of galaxies. The scale factor even hints at more exotic futures. Big Rip? Scale factor grows faster than exponential. Big Crunch? Scale factor eventually shrinks back to 0. It's all encoded in one variable. Simple, elegant, universal. Here's another beauty. The scale factor unites multiple observations. Supernova brightness, redshift of galaxies, cosmic microwave background. Each piece of data calibrates the others through the scale factor. It's a cosmic yardstick. One number that connects distance, time, and energy content. Matter, radiation, dark energy all influence how the scale factor evolves. It's the heartbeat of cosmic evolution. And it's not just theoretical. Every Hubble measurement, every redshift observation, every cosmic survey depends on it. Without it, expansion would remain a vague concept. With it, we can quantify the universe's past and predict its future. It's our bridge between theory and observation, from the fiery, dense beginnings of the cosmos to the far future heat death. The scale factor measures it all. It gives numbers to expansion. It gives structure to chaos. It turns cosmic history into a story we can calculate. The universe grows, and the scale factor grows with it. Every measurement, every galaxy, Every photon stretching across space-time is a testament to this one elegant tool. Next time you hear about the expanding universe, remember, the scale factor is the universe's ruler. It tells us where we were, where we are, and where we might be headed. A single number that defines everything in motion. And that's the power of cosmic math. Let's think about light. Not just any light, the light that traveled billions of years to reach us. Every photon carries a story, and the story is written in its color. When galaxies race away, their light stretches toward the red end of the spectrum. We call this redshift. Redshift isn't just pretty, it's a cosmic timer. It tells us how far back in time we're looking. A galaxy with a small redshift, close in space and time. A galaxy with a huge redshift, you're peering into the infant universe. Redshift is our clock for cosmic history. Here's how it works. Light has a wavelength. Stretch space, and the wavelength stretches too. The faster the expansion, the more it stretches. Measure that stretch. Boom, you have distance and time. A galaxy's redshift tells us how big was the universe when this light was emitted. How much has space expanded since then? Each galaxy becomes a timestamp, a photograph of the universe at a specific moment. Now imagine hundreds of galaxies, each at different redshifts. We can plot the expansion of the universe. It's like connecting dots across billions of years. Redshift plus distance, a timeline of expansion. This is how astronomers discovered accelerating expansion. Type Ia supernovae act as standard candles. Compare their observed brightness with expected brightness. The farther away they are, the fainter than expected they appear. The scale factor has grown faster than anticipated. Dark energy revealed itself through redshift measurements. Redshift isn't limited to distant galaxies. Nearby galaxies give us local expansion rates. Faraway galaxies reveal ancient cosmic history. Combine them and you get the full story. Redshift also reveals how structures evolved. Galaxies in the early universe appear smaller, clumpier, more active. Star formation rates, galaxy mergers, black hole growth, they all tie to redshift. Every photon is a piece of history. Every spectrum is a time capsule. Even the cosmic microwave background is a redshifted signal. Originally ultraviolet light, now microwaves. Redshift transforms it into a window on 13.8 billion-year-old events. It's not just a number, it's a map of change. We can reconstruct cosmic acceleration, deceleration, and the rise of dark energy. Redshift tells us when matter dominated, when radiation dominated, when dark energy took control. It's the ultimate chronometer. Every observation of a galaxy, a quasar, a supernova, is a tick of this cosmic clock. And by reading it carefully, we understand the universe's expansion history. Redshift transforms light into time, distance into story. It's why we can measure the Hubble constant, why we can test models of cosmic inflation, why we can predict the fate of the cosmos. In short, redshift is the universe talking to us. Its message? How I grew, how I changed, how I accelerated. Every photon is a word. Every spectrum is a chapter. Every redshift tells when and where in the cosmic timeline. Read carefully, and the universe becomes an open book. The next time you hear redshift, think cosmic clock. It's how we measure history, expansion, and the evolution of everything that exists. Imagine trying to measure the universe. It's not like measuring your room or even your city. We can't just stretch a tape measure across light years. So astronomers built a clever system, the cosmic distance ladder. Each rung measures farther than the one below it. Start close, then climb. Step 1. Parallax. As Earth orbits the Sun, nearby stars appear to shift against distant backgrounds. Look one way in January, another in July. That tiny shift, the parallax angle, gives precise distances. Stars within a few hundred light years, measured with incredible accuracy. Parallax is the first rung. It calibrates everything above it. Next, Cepheid variable stars. These stars pulse, expand, and contract in brightness over time. Their period is directly related to their intrinsic brightness. Observe the period. Calculate the true brightness. Compare with observed brightness. Boom, you get distance. Cepheids can be seen in galaxies up to 100 million light-years away. They are the second rung. Now we can calibrate the next rung. Type Ia supernovae. Exploding stars of remarkable consistency. All have nearly the same peak brightness. By measuring how bright they appear, we calculate distance across billions of light-years. Supernovae become our cosmic beacons. Each rung depends on the accuracy of the previous. Parallax errors? Everything above is affected. Cepheid errors? Supernova distances shift. Precision is crucial. The cosmic distance ladder also reveals the expansion of the universe. Plot distance against redshift. Near galaxies, small redshift. Far galaxies, large redshift. The slope gives the Hubble constant. This ladder is why we know the universe is billions of years old. Without it, we couldn't measure expansion. We couldn't test dark energy. We couldn't confirm cosmic acceleration. But it's not flawless. Different methods give slightly different Hubble constants. Local measurements, parallax plus Cepheids plus supernovae, suggest 73 kms MPC. Cosmic microwave background measurements suggest 67 kms SMPC. A small difference? 6%. Big deal? Yes. It hints at potential new physics, or hidden errors in our ladder. Either way, it drives cosmology forward. The cosmic distance ladder is more than math. It's storytelling across the universe. Each star, each supernova, each galaxy is a chapter in cosmic history, from nearby neighbors to galaxies billions of light-years away. The ladder shows how far we've come in understanding space. From parallax to supernovae, it transforms light into distance, and distance into understanding. It connects our backyard to the farthest reaches of the cosmos. Without it, the universe remains a dark, unknowable void. With it, we measure, compare, and predict cosmic evolution. Next time you hear cosmic distance ladder, remember, it's our stairway to the universe. Step by step, photon by photon, we climb higher, reaching further, understanding more. From Earth's orbit to exploding stars, we build the ladder, and through it, we measure the vastness, the history, and the expansion of everything. Subscribe to keep climbing the ladder of cosmic discovery. Ever wondered how fast the universe is expanding? You'd think one number would do it, one constant to rule them all. Enter the Hubble constant, named after Edwin Hubble, who discovered galaxies are rushing away from us. The faster they move, the farther they are. Simple, right? Measure distances, measure velocities, divide. You get the Hubble constant. But here's the catch. Different methods give different answers. Local measurements using the cosmic distance ladder, around 73 kilometers per second per megaparsec. Every million parsecs, galaxies move 73 km/s faster. Now, look at the cosmic microwave background, the leftover glow from the Big Bang. Early universe physics predicts a different value, 67 km/s MPC. 6% difference. Doesn't sound like much. In cosmology, that's a crisis. It's called the Hubble tension. Why the discrepancy? Some scientists say systematic errors. Maybe parallax angles are off. Maybe Cepheid calibrations are subtly biased. Or supernova measurements have hidden issues. Others think it's new physics. Perhaps dark energy behaves differently than we think. Or there's an unknown particle in the early universe. Maybe gravity isn't exactly as Einstein predicted over cosmic scales. The debate rages. It's intense, but exciting, because either way, we learn something profound. The universe is whispering secrets. Listen closely, and you might discover unknown cosmic rules. Why is the Hubble constant so crucial? It sets the age of the universe. Faster expansion? Universe is younger. Slower expansion? Universe is older. A 6% difference changes billions of years, and it affects everything. Galaxy formation, cosmic evolution, dark energy calculations. It's not just a number, it's a foundation for all cosmology. Even the methods themselves are fascinating. Distance ladder, parallax, Cepheids, supernovae, local, direct measurements, CMB, early universe physics, sound waves in primordial plasma, extrapolate to today, indirect, model-dependent measurements. Two methods, two realities. No one knows which is right. Some suggest both are right in their own way. Maybe the Hubble constant evolves over time. Maybe our local cosmic neighborhood is slightly atypical. Or maybe the universe has quirks we haven't uncovered. Every telescope, every measurement, every data point adds a piece to the puzzle. The controversy pushes scientists to refine techniques, recheck assumptions, rethink physics. It's science at its rawest, purest form. The universe is telling us, you thought you knew, but there's more. And we respond with obsession, calculation, and curiosity. So the next time you hear Hubble constant, remember, it's more than a number. It's a battle between observation and theory, between past and present, between what we know and what we might discover. A small tension, a huge story. And the resolution? It might rewrite how we understand space, time, and cosmic expansion. Keep watching the skies. Keep measuring. Keep questioning. Ever wonder how the universe got to be this big? It didn't just happen at a steady pace. Cosmic expansion has a history, and it's a dramatic story. Early universe? Fast and furious. Just after the Big Bang, everything was dense, hot, and energetic. Matter and radiation were crammed into tiny spaces. Expansion was rapid, but gravity was relentless. Matter fought back. Gravity tried to slow the expansion, and it worked for billions of years. The universe decelerated. Galaxies weren't flying apart as fast as they could. The scale factor, the cosmic ruler of expansion, grew slower than linearly. Time marched on, stars formed, galaxies coalesced. The cosmic web wove itself together. But about 5 billion years ago, something changed. A mysterious player entered the stage. Dark energy. It doesn't pull, it pushes. Repulsive gravity, invisible, uniform. Suddenly, the universe started accelerating. The scale factor grew faster than linearly. Space itself stretched at an increasing rate. Galaxies began receding faster than ever. What we measure today, a universe that's expanding more quickly now than in the past. The deceleration, acceleration, transition is written in the cosmos. We see it in supernovae. Distant supernovae appear fainter than expected if expansion were constant. They tell us, space expanded more than you think. We see it in the cosmic microwave background. Patterns of ancient photons reveal a universe once dominated by matter. And we see it in galaxy distributions. Large-scale structures record the tug-of-war between gravity and dark energy. Matter shaped the early universe. Dark energy shapes the late universe. Together, they write the story of cosmic expansion. Think of it like a cosmic tug-of-war. Matter pulls inward. Dark energy pushes outward. For billions of years, matter won, slowing expansion. Then, dark energy began to dominate, and now, push wins. The scale factor grows faster. Acceleration dominates the present. But the past matters. Deceleration by matter created the structures we see today. Galaxies, clusters, filaments, all born when gravity had its day. Acceleration by dark energy ensures the future will be a vast, expanding, lonely cosmos. Every redshift we measure tells a piece of this history. Galaxies with redshift 1, we see them as they were when the universe was half its current size. Galaxies with redshift 1090, we see the universe at 1/1000th its current size. Every photon traveling through space carries a story of expansion, deceleration, acceleration, matter domination, dark energy domination. It's all encoded, and it's mathematically precise. The scale factor captures the entire past expansion history. By fitting observations to theory, cosmologists know 68% dark energy, 27% dark matter, 5% ordinary matter. This combination explains the deceleration-acceleration transition, and it predicts how the universe will evolve. The past expansion history isn't just a curiosity, it's the blueprint for the future. It tells us how galaxies, stars, and life itself came to be. It tells us how cosmic acceleration shapes the universe's destiny. Understanding it is like reading the universe's autobiography, and the story is ongoing. So, watch closely, measure carefully, because every observation is a page in cosmic history. Let's take a journey forward, not a few years, not a few centuries, billions of years. The universe has a story to tell. Its future is as dramatic as its past. Cosmic expansion doesn't just stop, it keeps going. But how? That depends on dark energy, matter, and the laws of physics. First possibility, heat death. Imagine the universe as a battery, slowly draining. Stars burn out, galaxies drift apart, energy spreads thin, everything cools. The scale factor grows exponentially. Dark energy dominates. No new stars, no new processes. Maximum entropy, a cold, dark, lifeless universe. All that once was vibrant gone, a silent, cosmic graveyard. Second possibility, the Big Rip. What if dark energy strengthens over time? Not subtle, not gentle. It tears everything. Galaxies first, then star systems, then planets. Finally, atoms themselves. Space expands faster than anything can hold together. The universe literally rips itself apart. No structure remains, only the void grows. The ultimate cosmic destruction. Third possibility, the Big Crunch. Imagine the universe's expansion slowing. Gravity pulling harder. Dark energy fades or flips to negative. Expansion stops. The scale factor shrinks. Galaxies collide. Stars merge. Matter compresses. Everything collapses inward. A cosmic rewind. Perhaps another Big Bang awaits after the collapse. Cycles of creation and destruction. Each scenario depends on the balance of forces. Matter, dark energy, cosmic curvature, they all matter. The equations of general relativity provide the blueprint. The scale factor tracks the universe's growth or shrinkage. Observations today suggest heat death is most likely. Dark energy seems constant. Expansion is accelerating. We are heading toward a lonely, ever-expanding cosmos. But the other possibilities remind us. The universe is full of uncertainty. Physics gives us models, not guarantees. Future scenarios also show time's relativity. For distant galaxies, events may appear frozen due to extreme expansion. Acceleration shapes not only space, but perception. Even light itself struggles to cross vast distances. The cosmic horizon grows, then isolates. We may never witness the full unfolding of these futures, yet imagining them helps us understand why the universe behaves as it does today, why galaxies recede, why entropy increases, why dark energy dominates. Cosmic futures are not just science, they are philosophy too. They tell us about existence itself, about impermanence, about the fragility of structure in a growing universe. And they remind us, we are here at a rare, vibrant epoch. Galaxies, stars, life possible only because of this precise cosmic balance. The universe's story is written in the past, unfolding in the present, and shaping unimaginable futures. Every photon, every galaxy, every quantum fluctuation contributes to the tale. And we get to witness it. So look up, think big, because one day, billions of years from now, the universe will tell a story we can barely imagine today. But for now, it's alive, it's expanding, and we are part of it. Let's talk about one of the most famous mistakes in science. Albert Einstein, genius, visionary, and human. In 1917, he faced a problem. His brand new theory of general relativity predicted something shocking. The universe couldn't be static. It either had to expand or contract. But back then, everyone, including Einstein, believed the cosmos was eternal, unchanging, perfectly still. That was the scientific gospel. Einstein didn't like the idea of a moving universe, so he modified his equations. He added a term called the cosmological constant, represented by the Greek letter lambda. Think of it like a cosmic counterweight. Gravity pulls matter together, tries to collapse the universe. The cosmological constant? It pushes outward, just enough to keep the universe balanced. Static, eternal, elegant. For more than a decade, it seemed reasonable, until Edwin Hubble, Mount Wilson Observatory. Hubble measured the distances and velocities of distant galaxies. The result? Every galaxy is moving away from us. Not a few, not nearby ones. All of them. The universe is expanding. Einstein's static solution? Unnecessary. He called it his greatest blunder. But here's the twist. Fast forward to 1998. Astronomers studying Type Ia supernovae noticed something strange. The universe's expansion isn't slowing down. It's accelerating. Dark energy is pushing everything apart. Sound familiar? Yes, the cosmological constant, the very term Einstein discarded, perfectly explains this acceleration. The same repulsive force he introduced to prevent expansion now drives it. Einstein's blunder turns out to be incredibly prescient. Lambda wasn't a mistake, it was a glimpse into the energy of empty space. Every cubic centimeter of the vacuum contains a tiny amount of energy, insignificant locally, but across the cosmos, it dominates the universe. This tiny term outweighs all the stars, all the galaxies, all the matter combined. Einstein's intuition about space having energy was correct. He just applied it for the wrong reason. The cosmological constant now solves one of modern physics' deepest puzzles: dark energy. Yet, it also creates another mystery: the vacuum catastrophe. Quantum mechanics predicts a vacuum energy 120 orders of magnitude larger than observed. Why is the real value so small, yet powerful enough to accelerate expansion? Nobody knows. Einstein's blunder turned profound reminds us. Science is messy. Mistakes can be milestones. What seems wrong today may be revolutionary tomorrow. Cosmology evolves as we observe more, measure better, and refine our equations. Einstein's story also shows humility matters. Even a genius can misjudge reality, but the universe has a way of revealing the truth in time. So next time you hear about dark energy, cosmic acceleration, or the fate of the universe, remember, it all ties back to one man, one equation, one blunder. Sometimes, being wrong is the first step to being right. And yes, this cosmic irony makes the universe even more fascinating. Remember Einstein's cosmological constant? The one he added then called his greatest blunder? It's back. And this time, it's a hero. Fast forward to the late 1990s. Astronomers were tracking Type Ia supernovae, those brilliant exploding stars. They expected to see expansion slowing down due to gravity. Instead, the universe was speeding up, accelerating. Something mysterious was pushing galaxies apart. Dark energy. And what could explain this invisible force? The cosmological constant. The very term Einstein introduced for the wrong reason now fits perfectly. Think of it as a cosmic energy embedded in space itself. It doesn't dilute as the universe expands. It doesn't clump into stars or planets. It just sits there, creating repulsive gravity, stretching space at an ever-increasing rate. Lambda, once abandoned, became the leading explanation for dark energy. Observations of distant galaxies, the cosmic microwave background, and large-scale structures all point to the same conclusion. The universe is roughly 68% dark energy, and dark energy behaves exactly like Einstein imagined decades earlier. This term transforms the cosmic picture. Without it, our models fail to explain accelerated expansion. With it, we understand why galaxies recede faster than expected, why space itself grows exponentially in the far future. It's poetic irony. Einstein's discarded idea now shapes our understanding of reality. Even more fascinating, lambda is tiny but dominant. The energy in a single cubic centimeter of empty space is minuscule. Yet, multiplied across the universe, it overpowers all matter and radiation combined. This simple term has cosmic consequences. It determines the future of galaxies, the fate of cosmic structures, even the ultimate heat death of the universe. Without the cosmological constant, the universe might have slowed or collapsed. With it, expansion accelerates, carrying galaxies beyond the cosmic horizon. It challenges intuition. Empty space has power. Nothingness becomes a driving force of cosmic evolution. Cosmologists now use lambda in Friedmann equations, predicting how the scale factor changes over time. Exponential growth, accelerated expansion, and the heat death scenario all emerge from this single parameter. It also solves puzzles like the flatness problem, helping explain why the universe is so close to critical density. And here's the deeper lesson. Science isn't linear. A supposed blunder can lie dormant for decades before observations bring it to life. The cosmological constant shows how theory and observation dance together across time. Einstein's intuition about vacuum energy was ahead of its time. Modern instruments, measurements, and supernova surveys finally proved him right. It's a reminder: the universe often rewards curiosity, persistence, and bold thinking, even if initially dismissed. So when you think of dark energy, don't just see a mysterious force. See a story of discovery, irony, and the resurrection of an idea. A term once rejected now explains the most profound force shaping the cosmos. Cosmological constant. Einstein's blunder turned cosmic cornerstone. Imagine peering through one of the largest telescopes in the world, Mount Wilson Observatory, 1920s. Edwin Hubble, an astronomer with patience rivaling the universe itself, trained his eyes on distant nebulae. Back then, astronomers debated, were these clouds part of our Milky Way or separate galaxies? Hubble measured Cepheid variable stars inside these nebulae, stars that pulse with predictable brightness. By comparing how bright they appear to how bright they really are, he calculated their distance, and what he discovered shocked the world. These nebulae weren't part of our galaxy. They were entire galaxies, far beyond the Milky Way. The universe was vast, but there was more. Hubble measured the redshift of these galaxies. Redshift, the stretching of light as objects move away from you. Almost every galaxy he observed showed redshifted light. They were receding, every single one. Even more incredible, the farther a galaxy, the faster it moved away. Twice the distance, twice the speed. 3 times the distance, 3 times the speed. A pattern emerged. Recession velocity proportional to distance. Hubble's law. This was the first quantitative proof that the universe is expanding. Not just galaxies moving through space, but space itself stretching. Think of raisins in rising bread dough. Every raisin moves away from every other raisin. No central point, no edge, just uniform expansion. This overturned centuries of thinking. The cosmos wasn't static, it was dynamic, alive in a slow-motion ballet, across billions of light years. Hubble's discovery also gave birth to modern cosmology. For the first time, astronomers could map the universe in 3 dimensions. Before Hubble, astronomy was flat, just positions on the sky. After Hubble, the universe had depth, structure, and motion. His work answered one question and raised another. If galaxies are moving apart, what does this say about the origin of the universe? Every expanding universe points backward in time to a denser, hotter state. The seeds of the Big Bang were sown in his data even before the term existed. Hubble's constant, the proportionality factor in his law, became a key cosmological number. It tells us how fast the universe expands today. A larger value means a faster expansion, a smaller one, a slower expansion. Early measurements had errors, but the relationship itself was rock solid. Hubble's observations connected the observable to the theoretical. They confirmed what Einstein's original equations had predicted: a dynamic universe. The universe is not frozen in time. It evolves, stretches, and changes. Galaxies aren't flying through space. Space itself is expanding. This is why, even now, distant galaxies appear farther than we might naively expect. Light travels through expanding space, lengthening its journey, redshifting its wavelength. Every time we look at the night sky, we're seeing a universe in motion, a cosmic history written in light. Hubble's discovery didn't just expand our universe, it expanded human imagination. It showed that our cosmos is grand, dynamic, and astonishingly vast. And it laid the foundation for understanding dark energy, cosmic acceleration, and the fate of everything. So, the next time you look up at the stars, remember, they're not just points of light, they're signs of an expanding universe, a universe in motion, a universe alive with history and mystery. Imagine the universe as a tightrope walker. On one side, expansion, the relentless stretching of space. On the other, gravity, the invisible hand, trying to pull everything back together. Balance is everything. Cosmologists call this balance the critical density. It's the precise amount of matter the universe must contain to tip the scales between eternal expansion and eventual collapse. Too little matter and expansion wins. The universe drifts apart forever, galaxies slipping beyond each other's reach. Too much matter and gravity dominates. Expansion slows, stops, and reverses into a big crunch. Exactly the right amount? You get a universe that slows but never stops teetering on the cosmic knife edge. The critical density isn't a huge number. It's about 5 hydrogen atoms per cubic meter, barely anything. Yet, this minuscule amount spread across the vastness of space determines the fate of everything. Here's where it gets tricky. Most of the universe's matter is invisible. Dark matter, we can't see it, we can't touch it, we can't detect it directly, but we feel it. Galaxy rotation curves, gravitational lensing, cosmic structures, dark matter's gravitational fingerprints are everywhere. When scientists included dark matter in the cosmic balance sheet, they found that the universe has roughly 30% of the critical density in matter. That's not enough to stop expansion. Gravity alone cannot halt the universe's stretch. But then came dark energy, the ultimate wild card. Unlike matter, dark energy creates repulsive gravity. It doesn't pull, it pushes. It accelerates expansion instead of slowing it. This changes the game. Critical density now isn't just about matter. It's about how matter, dark matter, and dark energy interact. Current observations: the universe is about 5% ordinary matter, 27% dark matter, and 68% dark energy. A near perfect balance. Expansion and gravity, push and pull, creation and destruction woven together in a delicate cosmic dance. The universe is neither doomed to collapse nor guaranteed to drift into emptiness without structure, at least not yet. We are living in a golden epoch, a time when the densities of dark energy and matter are comparable. A rare window where galaxies, stars, planets, and life can exist. Cosmic coincidence? Maybe. Or maybe it's necessary. Life can only observe the universe during this delicate balance. Think of it. Billions of years from now, dark energy will dominate completely. Matter will be diluted, galaxies will be isolated, and expansion will rule unchallenged. The universe will still exist, but the delicate balance that allows observers like us to notice it will be gone. This is the cosmic knife edge, a balance of forces so precise that even tiny changes in the early universe could have produced a radically different cosmos. Too much expansion, too early, no galaxies. Too much matter universe collapses before life forms. Yet here we are, on the edge, witnessing it. The interplay of expansion and gravity doesn't just shape cosmic structure. It shapes existence itself. Every star, every planet, every atom is part of a universe hanging on a knife edge. And through the telescopes we build, the equations we solve, and the light we analyze, we glimpse the fragile harmony that makes life possible. Expansion versus gravity, a story of push and pull, of balance and precision, of a universe walking a tightrope across billions of years and light years. And we get to watch. The question isn't just how the universe expands, it's how we exist within that expansion. The cosmic knife edge isn't abstract. It's alive in every galaxy, every photon, every heartbeat. And it all started with a balance so fine, it might just be the most important number in existence. Close your eyes and imagine the universe. You see stars, galaxies, planets, maybe even yourself. Now imagine most of what exists can't be seen. That's dark matter, invisible, mysterious, yet everywhere. Galaxies spin faster than they should. Stars at the edges of galaxies orbit like they're on a carousel, spinning too quickly. Newton says they should fly apart. They don't. Something unseen holds them together. Something massive. Something gravitational. Enter dark matter, the hidden scaffolding of the cosmos. It outweighs ordinary matter by more than 5 to 1. Galaxies, clusters, even the vast cosmic web, they all rely on this invisible glue. Without it, stars would drift apart. Galaxies would crumble. The universe as we know it wouldn't exist. We can't see dark matter with light. It doesn't shine. It doesn't absorb. It doesn't reflect. Yet, its presence is undeniable. Gravitational lensing bends light from distant galaxies. Cosmic structures form in patterns that only dark matter can explain. Even the cosmic microwave background relic light from the Big Bang carries fingerprints of dark matter's influence. Scientists have tried to catch it. Detectors deep underground. Telescopes scanning for faint signals. Particles colliding in accelerators. Still, it remains elusive. No direct detection yet. It's a ghost, a shadow that shapes reality. But its effects are real. Without dark matter, the universe's balance would tip. Gravity from visible matter alone couldn't hold galaxies together. Expansion would tear them apart. Stars, planets, life, none of it would survive. Dark matter is cosmic architecture. Invisible beams holding up the universe's skyscrapers of stars. It interacts through gravity, silently guiding motion across billions of light years. Some theories suggest dark matter might be a new type of particle. WIMPs, axions, sterile neutrinos. The names are technical, but the idea is simple. Something unseen dominates the cosmic stage. Without it, the universe would look entirely different. Less structured, less rich. Dark matter is more than an astrophysical curiosity. It's the reason galaxies exist. The reason clusters of galaxies hold together. Even the cosmic expansion we observe today, the way gravity pulls back against dark energy, is shaped by dark matter's invisible hand. We are here, in part, because of dark matter. It's the hidden mass that makes the universe as we know it possible. Every time you gaze at the Milky Way, remember, most of what you see is riding on something you cannot see. Dark matter is the unseen force that built the cosmos, shaped its history, and holds the key to understanding the future. Without it, the universe would not just be empty space, it would be chaotic, collapsing, unrecognizable. Dark matter remains invisible, but its presence is impossible to ignore. It's the universe's secret architect, the quiet force behind everything we can see, the shadow that shapes reality itself. Imagine the universe as a vast stage. Galaxies, stars, planets, all the actors move across it. But what's moving the stage itself? Enter dark energy. Invisible, ubiquitous, mysterious. It's not just a player in the cosmic drama, it's the director. The force behind the accelerated expansion of space itself. Unlike gravity, which pulls, dark energy pushes. It has negative pressure. Yes, negative. It's counterintuitive, almost paradoxical. Gravity pulls matter together. Dark energy pushes it apart. And right now, the push is winning. For billions of years, matter dominated. Gravity slowed the expansion. Galaxies clustered, stars formed, structure emerged. Then, about 5 billion years ago, the balance shifted. Dark energy became dominant. Acceleration began. The universe stopped slowing. It started stretching faster and faster. Space itself expands between galaxies. Not galaxies moving through space, but space growing. Distances increase at an ever faster rate. Light from distant galaxies travels through this expanding space. Their light appears dimmer, more redshifted than expected. This is how astronomers first detected the cosmic push. Supernova explosions, measured across billions of light years, revealed a surprising truth. The universe isn't just expanding, it's speeding up. The culprit? Dark energy. It's everywhere. Every cubic centimeter of space carries this invisible energy, even empty space. Einstein once called this the cosmological constant, a repulsive effect of the vacuum. Today, it seems he was onto something. Dark energy behaves remarkably like his constant. Uniform, persistent, ever-present. It doesn't clump like matter. It doesn't collapse. It simply fills space and pushes. As the universe expands, the influence of matter decreases. Galaxies spread apart. Gravity weakens over cosmic distances. But dark energy remains constant, relentless. Its negative pressure grows more influential over time. Eventually, it will dominate all cosmic dynamics. The geometry of the universe depends on this invisible energy. Dark energy determines whether the universe curves, stays flat, or bends toward collapse. Currently, it constitutes roughly 68% of the total cosmic energy. Dark matter adds about 27%, and ordinary matter only 5%. The dominance of dark energy shapes the ultimate fate of everything. Heat death? Big rip? The exact scenario depends on how dark energy evolves. If constant, expansion accelerates forever. If increasing, galaxies, stars, even atoms could be torn apart in a big rip. Dark energy doesn't just dictate expansion, it sets the stage for time itself. It stretches the cosmic fabric. It isolates galaxies. It drives horizons ever farther apart. The observable universe shrinks relative to the full cosmos. Regions once visible vanish beyond reach. Light can never return. Even the cosmic microwave background will fade. Dark energy dominates not only space, it dominates our ability to see and know the universe. Yet, despite its overwhelming presence, dark energy remains invisible. No telescope sees it. No experiment touches it directly. All we know comes from its effects. The stretching of space, the acceleration of galaxies, the slow redshifting of ancient light. We live in the era of dark energy, the epoch where the cosmos itself is being pushed into a future beyond comprehension. The universe is no longer just a stage, it's expanding into itself, driven by an invisible hand. And that hand, dark energy, the quiet force shaping every cosmic heartbeat, the unseen director of reality's grandest performance. Picture the universe on a knife edge. Expansion versus gravity, a cosmic tug of war. This is the flatness problem. The universe today appears nearly perfectly balanced. Matter, and dark energy combine to create a density almost exactly at the critical value. Critical density, the threshold separating two fates, collapse into a big crunch or expand forever toward heat death. If the universe had slightly more matter, gravity would dominate. The cosmos would slow, stop, and reverse. If slightly less, expansion would accelerate unchecked from the beginning. Yet, here we are, nearly flat, nearly perfectly balanced. Why? The answer begins in the first fractions of a second after the Big Bang. Enter cosmic inflation. Inflation is a brief period of exponential expansion. The universe didn't just grow, it exploded in size almost instantaneously. Tiny quantum fluctuations stretched across enormous distances. Any initial curvature, no matter how pronounced, got flattened. Imagine blowing up a balloon. Tiny bumps and wrinkles flatten as the surface expands. Inflation did the same for the universe. What once might have been curved became almost perfectly flat. Distances expanded faster than light, not violating relativity, because space itself expanded. The flatness we observe today is a direct consequence. Inflation also solved other cosmic puzzles. Horizon problem, why distant regions look so similar. Monopole problem, why certain exotic particles are absent. Flatness problem, why the universe appears balanced on that knife edge. Inflation stretched tiny quantum seeds into the vast cosmic structures we see today. Galaxies, clusters, superclusters, all traceable back to microscopic fluctuations. Yet, the coincidence remains intriguing. Even with inflation, we live in a rare epoch where matter, and dark energy densities are comparable. A few billion years ago, matter dominated. In the far future, dark energy will dominate completely. We exist during a brief cosmic sweet spot. Some suggest this is selection bias. We can only exist in universes where observers are possible. Others ponder the multiverse. Perhaps countless universes exist with wildly different densities, expansion rates, or curvatures. Inflation makes our universe look flat, but it also hints at something bigger, a cosmos of infinite variety. The flatness problem isn't just math, it's a window into the first moments of creation. It's a reminder that our universe is finely tuned, improbable yet real. It's proof that the cosmos is more than random chaos. It follows patterns that can surprise, delight, and humble us. Inflation solved the flatness problem, yes, but it also left us with bigger questions. Why this universe? Why these parameters? And what other possibilities exist beyond our observable horizon? Understanding inflation is understanding the cosmic blueprint, the first brushstrokes of reality itself. Imagine this: our universe is not the only one, not even close. Infinite others might exist, each with its own space, its own time, its own expansion story. This is the multiverse, a concept that stretches reality beyond imagination. Why consider it? Because cosmic inflation suggests it. Inflation doesn't stop here. Quantum fluctuations create pockets, bubble universes, each inflating independently. Some expand faster, some slower. Some with stronger dark energy, some weaker. Some collapse quickly, others endure for trillions of years. Every bubble is self-contained, no communication between them. Each universe has its own laws of physics, its own constants, its own fate. Here's the twist. Quantum mechanics multiplies possibilities even further. Every decision, every random fluctuation, every particle interaction could create a branching universe. A universe where you made a different choice. A universe where stars formed earlier, or later, or never. Infinite variations of reality. Every cosmic scenario plays out somewhere. The Big Rip in one universe. A Big Crunch in another. An eternal, static cosmos. In yet another, our universe is just one patch in this infinite quilt. But what does this mean for us? It challenges the way we define existence. If infinite universes exist, does our history matter? Does our cosmic expansion matter? Or is it just one story among countless others? Yet, even in the multiverse, our universe is real to us. Our galaxies, stars, planets, and life. The expansion we observe is tangible. The multiverse idea doesn't erase our experience. It expands it. It hints that reality is bigger, more complex, more astonishing than any single universe can show. And here's the kicker. Some multiverse models might leave subtle clues. Collisions between bubbles could imprint patterns on the cosmic microwave background. Tiny anomalies in the sky might be fingerprints of other universes. So far, we haven't detected them. But the search continues. The multiverse isn't just science fiction. It's a natural extension of the physics we already observe. It forces us to rethink what universe even means. One finite, self-contained cosmos, or an infinite ensemble of realities, each expanding in its own way. Every distant star, every galaxy, every particle, our universe is part of a grand cosmic tapestry. And even if we can't observe the others, knowing they could exist changes our perspective. It reminds us how small we are and how awe-inspiring the cosmos truly is. The multiverse is a humbling, mind-bending possibility. It's a universe times infinity. It's cosmic expansion multiplied by limitless potential. And in that infinite stretch, somewhere, countless versions of reality, perhaps versions of you, are exploring the cosmos in ways we can barely imagine. Think about this. Everything you know, every memory, every fact exists in space. Atoms, molecules, neurons, patterns in matter and energy. Now, imagine space itself stretching. Distances between atoms, stars, galaxies, all increasing. What happens to the information stored in those patterns? Does it vanish? Does it survive? Here's the first clue. Local information suffers. As the universe expands, regions drift apart. Signals take longer to travel. Eventually, some regions can't communicate at all. Causal contact is lost. Your memories, your local patterns isolated. On cosmic scales, this is a form of information fragmentation. Pieces of the universe become practically irretrievable. But physics gives us a lifeline. Quantum mechanics flips the picture. Particles can remain connected across vast distances entangled. Even if galaxies drift billions of light years apart, entangled states stay correlated. Information encoded in these correlations persists. It's a cosmic tether, defying the stretching of space. Next, think bigger. The global picture. The universe itself keeps records. Cosmic microwave background radiation, galaxy distributions, space-time geometry, all encode the universe's history. Even as local patterns fade, the expansion history itself preserves information. Your memory might dissolve, but the story of the cosmos survives. Now, a paradox emerges. The more space grows, the more storage capacity the universe seems to gain. The holographic principle hints that all information in a volume can be stored on its surface. As expansion stretches space, surface areas grow. Potential for storing information increases. New structures, new complexity possible, even as old patterns fade. So expansion both dilutes and preserves. Local arrangements dissolve. Global patterns endure. Quantum entanglement bridges distances. Cosmic history is written into the very fabric of space. Yet, there's a sobering edge. Acceleration, driven by dark energy, eventually erases traces of the past. The cosmic microwave background redshifts beyond detection. Distant galaxies vanish from view. Future observers might conclude the universe is static, empty, eternal. All local evidence of cosmic history disappears. And yet, the information doesn't vanish, it's just beyond reach. Expansion creates a tension between what is physically present and what is knowable. The universe becomes its own memory system. Local information fades. Global cosmic patterns persist. Quantum states, space-time structure, cosmic evolution, they record the story. We are both participants and witnesses. Every particle, every galaxy, every observation we make adds to the universe's memory. Even as expansion stretches reality, the cosmos retains the echo of its own becoming. Information in an expanding universe is a dance between loss and preservation, local decay and global persistence, quantum entanglement and cosmic memory. And that balance shapes everything we know about our past and everything we can imagine about our future. Imagine a future civilization. They have technology, intelligence, curiosity, just like us. But the universe they inherit is unrecognizable. Galaxies beyond their local group have drifted away faster than light. Light from distant stars no longer reaches them. The cosmic microwave background stretched beyond detection. The redshift patterns that once revealed expansion, gone. Hubble's law, unmeasurable. To them, the universe appears static, small, empty, eternal. Everything that told the story of the Big Bang has vanished. Their scientific methods are flawless, but their conclusions are wrong. They will reconstruct a cosmos that never existed, from the evidence that remains. All that knowledge we take for granted, our cosmic history becomes inaccessible. And this isn't science fiction. This is the natural consequence of accelerating expansion. Dark energy doesn't just push galaxies apart, it stretches the information about the universe beyond observation. Think of every particle, every photon, every record of cosmic events. Expansion scatters them across the void. Causally, disconnected regions form. No signal can cross the gap. No information exchange is possible. Observational history fragments. Local patterns survive only temporarily. Long-term memory of the universe becomes practically impossible. Even the most advanced future civilizations will be confined to their local group. The universe shrinks in scope, not size. A single giant galaxy may seem like the entire cosmos. Everything beyond fades into irrelevance, not because it disappeared, but because it is unreachable. And here's the irony. Knowledge itself is physical. It exists in arrangements of matter and energy. As space stretches, these arrangements disperse. Conscious beings, stars, civilizations, all become isolated islands in a vast, empty sea. The very tools to understand the cosmos, the light, the radiation, the cosmic patterns, vanish beyond the horizon. Knowledge is not destroyed. It is simply beyond access. And yet, there's a subtle beauty in this. The universe doesn't erase its history. It just reshapes what can be observed. Information is preserved in the structure of space-time, in the quantum states of matter, in the cosmic web we currently study. Future observers might not see it, but it exists. Expansion teaches a profound lesson. Knowledge is tied to perspective. The story of the cosmos is only visible if you live at the right time, in the right place. Our era, the era of billions of observable galaxies, is unique. We are privileged witnesses. We have the opportunity to see the universe in its richness. And perhaps, by recording what we know, we can ensure that knowledge transcends the limits imposed by cosmic acceleration. Cosmic expansion doesn't destroy history. It challenges us to recognize its fleeting, precious nature. The universe may outlast all observers, but knowledge can echo beyond the stars if we act now. Take a moment, breathe, look around. Everything you see, space, time, matter, energy, is part of a story still being written. The universe isn't just growing, it is creating itself. Expansion is not movement into empty space. It is the unfolding of space itself. There is no outside, no cosmic stage beyond the cosmos. The universe is both stage and actor. And here's the mind-bending part. We are part of it. Every thought, every heartbeat, every action interacts with the expanding cosmos. We are not passengers on a cosmic ride. We are participants in the very act of creation. Every observation we make, every discovery we record, is an imprint on the universe. Our existence, consciousness, and curiosity are part of the unfolding expansion. The galaxies we see, the stars we study, the cosmic microwave background we analyze, all of it is more than data. It is a reflection of reality, becoming aware of itself. Imagine that. The universe knows itself through us. Our questions about dark energy, black holes, and cosmic expansion aren't just scientific. They are existential. They are the universe turning inward, asking, "What am I? What am I becoming?" Each discovery is a mirror. Each insight is a dialogue between us and the cosmos. Expansion is infinite potential. Not infinite in a mechanical sense, but infinite in possibility. Every cubic inch of newly created space carries opportunities for matter, energy, structure, and life to emerge. And we are evidence that the universe can reflect on itself. This perspective reshapes meaning. It isn't about a destination like heat death or the Big Rip. It's about process. The journey of space stretching, stars forming, galaxies colliding, civilizations arising. All of it is the universe experiencing itself. We are not separate from expansion. We are expansion aware. We are space contemplating space, time reflecting time, energy exploring energy, and that changes everything. Science gives us facts, cosmology maps the mechanics, but philosophy connects us to the story. We are not spectators of a distant drama. We are the drama. We are the questions, the observers, the participants. The universe expands, and in its expansion, it has created minds capable of wondering, questioning, and marveling. Every discovery, every insight, every awe-filled moment, that is, the universe recognizing itself. So, as we conclude this journey through cosmic expansion, remember, we are not just in the universe. We are the universe unfolding. We are space and time awakening. We are part of the infinite creative process. And that, perhaps, is the greatest truth of all. If this cosmic journey inspired you, don't forget to subscribe and join us in exploring the mysteries that lie ahead.